Good evening, my dear warriors. All the warrior Pandus quickly start trending WP. I can see so much of fire in the chat box already. Thank you so much. Happy evening. Good evening, my dear lovely warriors. I hope you guys are doing great. Yes, hi Capto. Hello everyone. Yes, your Captain Shreyas is here. And this is one of the most important chapters, I believe, for every competitive examination, and often also most misunderstood. So why not create this special session, midnight session? It's going to be a long session. I hope you had your dinner and I hope you're not going to sleep. Just make that promise to me, right? I'm very good, thank you so much, and happy Navratri again. And yes, sir, OP for conducting this midnight class for all of you. For those of you who do not know me, here is my small introduction slide. Yes, and if you're not yet smash the like button, please do that right now. Okay, so I want full concentration because I'll be full in the flow, and yes, we will keep it very lively, very engaging, with lots of examples, theory, concepts, applications, and also I'll give you an idea of how NTA will set the paper by giving you those level of questions as well. So complete lesson right from the basics of your rotational motion and rigid body. Okay, so let's begin, guys. Awesome. Yes, Capto is very fine. Thank you so much, guys. Welcome. Good evening. So let's begin with the class. Just 1 second. Okay, chalo. So let's begin. So what are we going to exactly start our class with? See, I'll tell you the flow of the class. We will start off with the concept of moment of inertia. Then we will go to the concept of basically, your energy. We'll go to the concept of energy, moment of inertia, energy. Then we'll go to the concept of angular momentum. Then we'll go to the concept of basically torque, and then we will take a mixture of questions. So it will be a mixture of concepts and conservation of momentum, conservation of energy, and all those things. So that is our basic flow of this particular class today. Okay, now one thing peculiar about rotational motion, and how do you distinguish with translatory motion? See, imagine you had a body like this, and you find that every single point on the body moves exactly the same amount, basically same displacement for all the particles. Then such a motion is basically called as your translatory motion. This is called as translation. Very simple. All the things should move by the same amount. For example, I have this nice water bottle with me. Imagine it is translating, it goes like this. It is translating, it goes like this. It's translating, it goes like this. Every single point moves by the same amount. If the bottle moves 3 meters, this also moves 3 meters. The cap moves this 3 meters, it should move 3 meters. Every single point should have the same displacement. Then such a motion is basically called as translational motion. But in case of rotational motion, it is slightly different. You will not see that they are moving the same displacement. Rather, every particle on such particular body, if it is a pure rotational motion, then you will see they will have same angular displacement. For example, Shreyas sir, after teaching so much, Shreyas sir lost his cool and Shreyas sir is acting very weird. Shreyas sir is rotating like this. My head will rotate by 90 degrees. My hands will rotate by 90 degrees. My trunk of the body will rotate by 90 degrees. Nose will rotate by 90 degrees. Every single particle will rotate by the same angle. So if I was here, I rotated like this. Maybe my hands moved a little bit more, nose moved little bit less, displacement wise, but angle wise, it is the same. So basically same angular displacement, then that is called as a pure rotational motion. That is called as rotational motion. Okay, rotational motion, guys. I hope this distinction is very, very clear. Everyone? Yes. So toppling, rolling, yes, we'll be doing that as well. Yep. Okay, great. Yes, awesome. Now, when you combine both of them, that is called, a combination of translation and rotation. For example, Shreyas sir, after teaching so much, he is not just rotating, but he is also going somewhere and all. He is going somewhere and all. So I am not just moving, but also I am rotating, guys. So that's a combination of translation and rotation motion, right? So now that you understand this particular concept, you realize one more interesting thing. Whenever rotation happens, there is a point about which it rotates. This point is what I will call, I'll put it over here in the next slide. So if I have some particular body and it rotates maybe about some particular point, all the points on that particular body move by some amount, some angular displacement like this. So that point about which they rotate is basically called as the axis of rotation. Now please mind it, axis need not be always inside the body. The axis can be even outside the body. So here the axis is outside that particular body. It can also remain inside the body. It could be anywhere. It doesn't really matter. So in such a case, if it is outside, it just means all these particles are going in circles like this. They are going in circles like this. They are just going in circles like this. All about this axis. This body is rotating like this. This body is spinning over here like this. This is like spinning, rotation. This is like revolution, something like that, because the axis is outside. That's all. Okay, I hope this is very, very clear. Now, no matter what, whether the axis is outside or inside, as long as it is a rotating body or it is a rotational, as long as it is a rotational motion, since all the points have the same angular displacement, all the particles move by the same angle. So let's focus our attention on any one such point. Maybe it is located over here, maybe some other point which is located over here, or maybe some other point which is located over here. Same thing over here, some point located here, some point located here, maybe some other point located over here. These green dotted lines, what are they? They are the distance of those points from the axis. They are the distances of those points from the axis. Each point will have a different velocity, not angular, velocity. So maybe this point has some velocity like this. Maybe this point has some velocity maybe like this. Maybe this point has some velocity like this. 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 So these are the velocities of those particular points. One thing very peculiar which you can see, the velocities are perpendicular to the distances from the axis. Has to be. The velocities will be perpendicular to the distance from the axis. Why? Because each point will go around a circle, and this is the radius, this is the circumference. Radius is perpendicular always to the circumference. Is that making sense to all of you? Same thing, this particle will go in a different circle. This particle will go in a different circle. But everywhere you will see the velocity will be along the circle, and this dotted lines will become the radius of that particular circle. Same thing even here, it is going around a circle. Even this is going around a circle. So all the points are going in circles, so the velocities are perpendicular to the distances which act like the radius. So can I say, my dear warriors, this distance from the axis is basically r, this velocity is v, and it will have some angular velocity omega. Each of these points will have some velocity v, some distance r, and angular velocity basically omega. Since it is just rotating, and all the points have same displacement in the same time, which means what will be same? Put it up in the chat box. Which will be same, guys? Yes, think about it. If they rotate by the same amount. You can always replay the same part, guys. You can just go behind and you can, if you want anything to be repeated, yeah. What will be same? Omega will be same angular displacement, which means omega is same for all particles, It's very, very obvious. And because of that, since we know V is nothing but omega into R, where did you study this relationship? You studied this in circular motion. You have studied this relationship in circular motion, right? So I can just block this off. V is equal to omega R, which also means one more thing. Since R is different, since R is basically different, can I say the velocity is also different for different particles? The velocity is also different for different particles. If R is small, velocity is small. If R is big, velocity is big. Closer the particle, the speed is less. If the particle is far away, the speed is more. Which makes sense. If I rotate my hand like this, just imagine this. My hand is rotating like this. This point here is hardly moving with small velocity. This point here is having large velocity. The closer you go to the axis, the speed is small. As you go far away to the axis, from the axis, you can see the speed is more. So that's why you can see velocity is directly proportional to the distance from the axis. But what is same? Omega is same. Yeah? Yes. I hope this is clear. Okay. Parikshit, I hope this is clear. Krishna, Luru, yes, everyone. Okay. So, shall we proceed ahead? Okay. So, omega is same because displacement is same in the same time when my hand rotates, right? So, angle covered is theta, time is t, theta by t is omega. So, omega is same, right? Makes sense. Great. Awesomeness. Now, let's say I give you a question based on this. You'll be like, sir, so quickly? Yes, let's say I give you a question based on this. And I tell you, listen, there is some random body over here, and it is found that there is this axis of rotation somewhere over here, and it is told to you that this particular distance is 2 meters, this is, let's say, 6 meters, and this point has a velocity, of 5 meters per second. Can you figure out what is the velocity of this point over here? What is the velocity of this particular point over here, right? Since it is a rotating body, and we can already see that this is basically our axis of rotation. Hence, the omega will be same for all. Angular velocity will be same for all. And what is omega? It is always velocity divided by the distance. Velocity divided by the distance from our axis, basically r. So, V was omega r, or omega is V by r. Therefore, omega will be equal to, speed at this point is 5. The distance from the axis is basically 2. Speed at this point I don't know. R is basically 6. Therefore, V will be equal to, take 6 on the top, 6 multiplied by 5 by 2. 6 by 2 is 3, 3 5s are 15. So, velocity is 15 meters per second. So, speed is nothing but 15 meters per second. Everybody got this? Understood? Clearo? Perfect? Awesome, awesome, awesomeness. Now, I can make another beautiful question and you will like this, guys. Imagine it is mentioned to you, something like this, that hey, there is a body in this particular shape, and let's say the width of it is maybe 5 meters, the height of it is basically 4 meters, and it is also told to you that, listen, there is a point over here and it has a velocity maybe like this, okay? It has maybe a velocity like this. And it is also told to you, that there is a point maybe somewhere over maybe here, and the velocity is like this. And nothing is mentioned about the speed or what is the magnitude of the velocity. We just know this is velocity number 2, this is velocity number 1. Can you find the axis of rotation? Can you find the axis of rotation just based on this particular information? Can you just find the axis of rotation just based on this particular information? Let's just go back a little bit and see what is happening in all these scenarios. You will notice one thing in common, that the velocity at any point is directly perpendicular to the distance, from the axis, basically r. So using this property, I have an idea that wherever the axis is, I don't know where it is, but wherever the axis is, it must be perpendicular to the velocity. That means it will be somewhere on this dotted line. It will be somewhere on the dotted line. Maybe it is here, maybe it is here, maybe it is here, or here, or here. Everybody agrees? Also, since the axis is, the line joining the axis distance is perpendicular to every single velocity, if I draw perpendicular here, so the axis will be somewhere on this perpendicular also. Now, obviously, since I have drawn both the perpendiculars, they are going to meet somewhere. Yeah, guys, don't spam. Concentrate on the class. Yeah, somebody was spamming. So they will meet somewhere. Wherever they meet is the exact location where the axis must be. Hence, the axis is basically the point of intersection of the perpendicular which was drawn to the what? To the velocity vector. So this was the velocity. I drew a perpendicular here. Wherever they intersect, that's the common point where the axis must be. Is that making sense, everyone? Got it clear? Very good. Awesomeness. Now, not just that. Imagine you want to find the speed of any other point. All you need to do is just, let's say I want to find the speed of this point. So this is basically your r, and the velocity at that point would be exactly like this. It would be perpendicular to this. Any point, you just draw the line, perpendicular will give me the velocity at that point. Is this concept of axis of rotation, velocity and omega absolutely clear in your head? Give me a thumbs up, smash the like button if you have not yet marked your attendance, subscribe to the channel as well. Okay, done, understood, clear. And yeah, before I forget, one quick information, guys, regarding the MVSAT examination. In case you do not know about this, let me quickly tell you. The link is there in the description box below. Just open up the MVSAT registration site, because the online MVSAT scholarship test is going to start from 10th of October. Offline is almost over, still remaining in few cities. You will be competing with lakhs of students. You will be also getting prizes as well as scholarships up to 100% on many Vedanta courses which you eagerly want to enroll. If you are just enrolled, you will get a refund of that scholarship amount, so don't worry. And study material for those who attend the test, online, offline, wherever. And there is also a lot of goodies to be won, lot of prizes to be won. So guys, report card will be given to you, a proper ranking with detailed analysis. So don't want to miss this opportunity. Make sure you are registered for the MVSAT. Link is there down in the description box. Open that link, register with your mobile or email and all those things. It's very simple. It will hardly take a minute. Okay. So just reminding you, because or else you will forget this and suddenly that exam will go. It's free of cost and you'll be like, I could have just given that one something, known where I stand, because exam is just around the corner. Okay. Awesome, guys. Perfect. Now that we have understood till this particular point, let's move ahead to the next interesting thing. And we will come to something very cool and you will be like mind blown after whatever I'm going to do over here. Okay, so get ready for this. Say for example, there is a mass and it moves with some velocity. the kinetic energy of that particle is going to be half mv square. This is basically our kinetic energy of a translating mass, of a translating mass. But since we are doing the chapter of rotation, you will be like, sir, what is the rotational kinetic energy? Okay, so let's come to that. Now there is a small problem with rotational energy. You will be like, sir, what is the problem, sir? Okay, I will show it to you. Imagine, okay, 1 second. Imagine this is our body. Imagine this is our body. Okay, this is our body. Let me also show the axis of rotation. Let's say the axis of rotation is this one. So this is our axis of rotation and it is rotating with some angular velocity, let's say omega. The problem is every point on that body is at a different distance. Every point on the body is basically at a different distance from the axis, because of which every point has a different speed. Every point has a different speed in different directions. Do you guys agree with it? So if I want to find something called as the rotational kinetic energy of the body, rotational kinetic energy of that particular body, then that kinetic energy of rotation will be kinetic energy of every single particle. So it will be like K1 plus K2 plus K3, like that n particles for all the n number of particles. For all the n number of particles, you find the kinetic energy and you add them. Some will be K1, K2, K3, K4, K5, K6, like that. You add all of them, you will get the total kinetic energy of the body. Why K1, K2, K3 are different? Because, you know, each point is at a different place. Mass could be different, speed could also be different. Everybody gets this. Okay, sir, what is the value of K1, sir? The value of K1 is, maybe this point mass has a mass m1, the speed is v1. Mass m2, speed is v2. Like that till the last term, mn vn square. Mn vn square. Like, okay, sir, what is next, sir? Look at it carefully. v1, v2, v3, vn. What are these speeds? v1 is r1 into omega. v2 is r2 into same omega. Same thing, vn will be rn into that same omega. Omega is the same. Oh, very nice, sir. So what do we do now? Well, put it up over there and see what you get. You will get half m1. Instead of v1, you get r1 square omega square. Next, half m2 r2 square omega square. Last term will be half nth mass rnth distance square omega square. What is common in all of them? What is common in all of them, guys? Omega square and half. So I am getting m1 r1 square plus m2 r2 square, like that till mn rn square into omega square. Into omega square. Is that right, my dear warriors? Is that right, my dear warriors? Till this point, absolutely clear. This is the kinetic energy of rotation. Sum of m1 r1 square plus m2 r2 square plus mn rn square, omega square is outside, half is outside. Now I start using my brain a little bit and look at this and say that, oh, kinetic energy was half mv square. Okay, kinetic energy is half something into omega square. Then it suddenly clicks me that, wait a minute, if you talk translational motion and compare it with rotational motion, we already had few things which resemble each other, just the symbols and the units were different. For example, here we had angular displacement. Sorry, not here, here. Here we had angular displacement delta theta And here we just had the term displacement, which symbol was S. Then we had the term velocity over here, which had the symbol, sorry, this was angular velocity, my bad. Angular velocity, which was omega. Here we just had a velocity, which was V. Then we had angular acceleration, which had the symbol alpha. Here we had just simple acceleration, which had the symbol A. Everybody remembers this? Correct. So, if we have a term for mass, which is m, shouldn't there be an equivalent term for mass in rotational motion? Yes, there is. And that is nothing but called as the moment. Moment is associated with rotation. Moment of mass is nothing but inertia. So this is nothing but the inertia of the body for translation. This is moment of inertia. That means the inertia in rotation that has the symbol I. That has the symbol I. And the best way to see that is the kinetic energy of translation. If it is half mass into V square, the kinetic energy of rotation will be very identical. Instead of velocity, I will get angular velocity. Instead of velocity, I get angular velocity. Instead of mass, I should get moment of inertia. So instead of half mass V square, I get half I omega square. Oh, wait a minute, sir. That means this term inside the bracket, what should it be? What should it be, guys? Yes, it's the mass equivalent, mass analog. Yes, it's the equivalent of mass, but in rotation. So this term over here is the moment of inertia. This is how the definition of inertia comes into play for rotation. If you thought, sir, how did that person realize the formula is m1 r1 square plus m2 r2 square, etc.? Well, this is how that person realized. I hope this is absolutely clear. Everybody with me? So this is the kinetic energy of rotation. Obviously, the kinetic energy of translation. This is the kinetic energy of translation is half mv square. As simple as that. So this brings me to the main point, which is the moment of inertia. Moment of inertia. This moment of inertia, symbol is capital I, is the equivalent of mass, but in rotational motion. What does it tell you? It is basically going to tell me the tendency to oppose the change of state, change of the state of rotation. It is going to oppose the change of state of the rotation. And it completely depends on three things. It depends on three things. It depends on three things. You would have seen that right over here. Each of the masses, their distances from the axis, and that means it depends on the axis also, right? So all these things it will depend on. So it depends on the masses, where they are, that means the distribution, and obviously if the axis changes, each of the term changes. So that means it also depends on the axis of rotation. And the formula for moment of inertia, is m1 r1 square plus m2 r2 square, like that till mn rn square. That's the formula for moment of inertia. If you ask me what is the unit of moment of inertia, kg and meter square, so it is kg meter square in SI. In CGS it will be gram centimeter square. So if the masses change, obviously moment of inertia changes. If the distribution changes, that means R1, R2, R3, some mass moves away, some mass comes close. So obviously you will see moment of inertia will change. If axis changes, obviously R1, R2, R3 will change. If instead of this axis, that axis is used, obviously the moment of inertia will change. And the unit is kg meter square. Is this absolutely clear till this point? Yep. These are the three things. This is the unit and this is the formula. But this formula is okay if the masses are separate. There are two kinds of bodies. If you remember, we have done that in center of mass also. One mass is here, another mass is here, another mass is here. You can pinpoint. There are 10 masses. Then you will use summation. This system is called as a discrete system. This is called as a discrete system because you can count the number of particles. There are 5 atoms rotating. There are 5 point masses rotating. There are 50 masses rotating. Fine, you can use this. But imagine I'm rotating this bottle. This bottle is made up of countless particles and each point mass is dm, dm, dm mass at separate distances. So in such a case, what will you do? Instead of summation, what symbol will come, my dear warriors? Instead of summation, what symbol will come? Yes, you will get the symbol of integration, but this masses will now become dm and you will be integrating that distance r, which will be variable. So integration of r square dm will be the answer. That is for continuous body system. That is for continuous body systems. This is for separate masses. This is for continuous body like a sphere, hemisphere, cone, solid, cube, those kind of things, sheet. They are made up of countless particles. Yes, integrals will be used. Perfect, guys. So let's start taking up some questions. Let's start solving some problems as well. Okay, here comes the first question on your screen. Okay, so what do we have over here is basically some axis and some distances are of course given to us. Oops. This is 2 meter, this is 2 meter, this is 1 meter, or this is 3 meter, this is 1 kg, this is 2 kg, and this is 3 kg. These are the distances. This was the axis. It is given that it is rotating like this. So the question is, find the moment of inertia. Question is, find the moment of inertia of this particular system. Moment of inertia tells you how much it does not like to change its state, just like I told you over here. It is the tendency to oppose the change of state. If I try to rotate it, it doesn't like. How much does it not like? How much does it oppose the tendency? That is called moment of inertia, the equivalent of mass, but for rotation. Right. So let's try to solve this question, my dear students. You can see there are countable number of particles, so obviously summation symbol will be used. So in this case, there are 3 masses, so it will be m1r1 square plus m2r2 square plus m3r3 square. 3 masses, enough. Okay, mass number 1 is, let's say, this guy, so it is 3 kg, distance is 2 meter. Second mass, it is basically 1 kg, distance is 3 meters. Next mass, mass is 2 kg, distance is 1 meter. So square it, right? So 3 kg, 2 square, 1 kg, 3 square, 2 kg, 1 square. Perfect. 2 square is 4, 4 threes are basically 12. 3 square, 9, 9 into 1, 9. 1 square, 1, 1 into 2, 2. So 12 plus 9, that's 21, plus 2, that's going to be 23 kg meter square. 23 kg meter square. Yes. Got it, my dear warriors? Perfecto. Yes, 23 is the correct answer. Many of you got it. Awesome. Awesome. Great. Let's go to the next question. Let's go to the next question. It's a very interesting question. Let's see if you guys can figure this out. I will give you 3 or 2 some situations and you have to just compare which has more moment of inertia or less moment of inertia. That's all. Okay. This is situation number 1. This is situation number 2. This is situation number 3. In situation number 1, this is R, this is M. This is 2R, this is 3M. Situation number 2, this is R, this is M. this is 2r, this is 3m. Situation number 3, m is over here, and you can see 3m is again on the axis. 3m is again on the axis. Compare their moment of inertias. That's the question. Compare their moment of inertias. That's the question. Come on. Put up that symbol equal to, more than, less than, whatever you think it is. Whatever you think it is. It's just that some positions have been changed. That's all. The places have been changed. The locations have been changed. So what do you think is the correct comparison for the moment of inertia? Over here, even if you measure the moment of inertia, or over here, the thing is, I think it will be equal. I1 and I2 will be equal, because it will be just m distance square plus mass into basically distance and then square. Nothing else. How does it matter whether this 3m mass is here, or this mass m is here or here? How does that side matter? It won't matter at all. So guys, I1 and I2 will be equal. But if you look at the moment of inertia of the third mass, well, the r is only 0. So m into 0 square plus 3m multiplied by 0 square. So actually it is 0. So very, very obvious answer now. I1 will be equal to I2, which will be more than I3. I3 equal to 0. That is the correct comparison. Is that right? Everyone with me? So it's not that 1 is more than 2, or no, 1 and 2 are actually the same. Yes, so the side does not matter. Okay, so the side, which side they are, that really does not matter. Keep that in mind. Great. So that is how moment of inertia works. Now, let's do another question, guys, coming up on your screen. Let's do another question. Let's see if you can solve this question. The question is as follows. There is a mass m over here, and it is separated by another mass of mass, let's say 3m over here. The question is, find the moment of inertia about the center of mass. That is the question. You have to find the moment of inertia about which point? The center of mass. About the center of mass. Very, very interesting question. Yeah, even if you guys are joining in late and joining in new to the channel, first of all, subscribe and like the video so that next video, next class of Shreyas sir, you don't miss, number one. Number two, even if you're joined in late, don't worry, you can watch the previous part as a recording, okay? Just make sure you're attending the live. In case you do not have any idea about the topic, then even in the live class, you can go behind and start watching from the beginning, because that option is there on YouTube. Okay, so how do we do this question? Moment of inertia about center of mass. Let's try to understand the problem first. Where is the center of mass? The center of mass will be somewhere over here, more closer towards the bigger mass. That's what it is. But how much is this distance going to be? And how much is this distance going to be? I do not know that. Without finding R1 and R2, I can't proceed and solve the problem at all. So first step is to find what is R1 and what is R2. How do I find that? It's completely up to you guys. I mean, you can use different methods. Let's say you consider the origin only to be the center of mass. Let's say you consider the origin to be the center of mass, right? So if you do that, this is our x-axis, okay? This is our y-axis. This is our origin. So as per the definition of center of mass, x coordinate of the center of mass will be m1 x1 plus m2 x2 divided by m1 plus m2. That is the formula. What is the x coordinate of the center of mass? The origin itself. So it is 0. What is mass number 1? 3m. What is the x coordinate of it? It is basically r1. What is mass number 2? It is basically m. What is the x coordinate of it? It is basically r2 but with a negative sign. It's on the other side. And the whole thing divided by m plus 3m. Perfect. But it doesn't matter. Numerator has to be 0. So therefore, just shift this guy over here. So m r2 will be 3m r1, or rather R2 will be 3 times of R1. R2 will be 3 times of R1. But you don't know what is R1. So what do you do now? Next step, just check that out. R2 plus R1. This plus this is the total distance. So it is equal to R. That's about it. And R2 is nothing but 3 times of R1. So therefore, R1 is nothing but R by 4. If R1 is R by 4, that also means R2 will be 3 times of R1. So it will be 3 times of R by 4. So I got the values of R1 and R2. Now I can proceed with the problem. Finally caught up, some of you. Very good. Yes. Not 2 by 3. Some of you thought it would be 2 by 3. No. So it is not. It is basically R by 4 and 3R by 4. Let's use that over here now. So R1 is R by 4. This is R by 4 and this is 3 times R by 4. So moment of inertia will be first mass 3m, distance R by 4 square plus second mass m. Distance doesn't matter positive, negative, it is anyways going to get squared. That's one big difference with center of mass. In center of mass, positive negativity matters because it is x1, x2 coordinates. But in moment of inertia, they are anyways squared and they are distances which are always going to be positive. That's all. So this will become 3mr square by 16 plus 3 square is 9. So 9mr square, 4 square is again 16. So 3 plus 9, that's going to be 12, and 12 by 16 mr square. 12 goes with 4 3 times, 16 goes with 4 4 times. So 3 by 4 mr square is the answer for the moment of inertia. That's it. 3 by 4. Is that clear, everyone? Understood? Is that absolutely clear? Yeah? Shall we go ahead? Yes? Shall we go ahead? Let me know if you understood all these basic problems of moment of inertia. Yes, 3 mr square by 4. That's the correct answer. Now, what about finding the moment of inertia of other things? These were just point masses. Sir, you still did not do any question on the integration part, sir. What about this formula? You did not use it anywhere. Okay, so for example, say I have to find the moment of inertia of basically a ring. Moment of inertia of basically a ring. So this is our ring. This is our axis, something like this. If you take any mass on that ring, it's going to be a point mass and there are many masses, so I have to use integration. That dm mass will be at the same distance as that of the radius of the ring. Whatever is the radius, right, of that particular ring, let's say it is capital R. So all masses, I will say, all point masses. What are those point masses? dm are at the same distance from the axis of rotation. And what is that distance? The distance is basically the radius of the ring. That's the best part of the problem. So when I use this I is equal to integral r square dm, the problem becomes very easy. Small r is capital R and capital R is same. So integration demands us to bring it outside the symbol. So that's it. It will be just integration of dm. Integration of dm signifies I am adding all the masses on the ring, which boils down to basically the mass of that ring, which is nothing but capital M or small m or whatever it is. Okay, so if the symbol is m, so hence the moment of inertia of the ring will become mr square. So this is the moment of inertia of a ring. Very, very important, guys. And this comes via simple derivation of the integration. Is this absolutely clear, everyone? Is this absolutely clear, everyone? Very good. Now, if this much is understood, then can we also find the moment of inertia of basically a rod, moment of inertia of basically a rod. Let's try that out. So let's say this is a rod like this, and let's say somebody is rotating about this particular axis, okay, in this particular manner. This is the mass m and the length of that rod is basically L. I want to find the moment of inertia of that rod. Again, the rod is made up of many point masses. The rod is rotated about its end. So what do I do? I'll take a point mass. That point mass is dm and the distance from the axis is basically, let's say, x, or let's say basically r, doesn't matter, r. So the moment of inertia totally is integral r square dm. But the problem is I can't integrate this. This is r, this is m. I can't integrate r with respect to m. I hope this is absolutely clear, everyone. Just one second. Okay, now the problem is, how do I convert this? I'll tell you what, this is a linear body. And I have told you something about, what is the thing that you do while integrating and how to choose the elements for linear bodies. For flat aerial bodies, laminar, sheet-like bodies, you use sigma, aerial mass density. For big bodies, you use rho, which is volumetric mass density. For wire-like objects, you use linear mass density. Remember this? Yes, linear mass density. Yes. So, guys, that means I have to use this symbol, lambda, which is nothing but dm by dr, mass per unit length, which is also the total mass upon the total length. Rearranging, I just get dm is nothing but m by L multiplied by dr. This helps me a lot because it will now become r square capital M by L dr. I know m and L are constants, so put it outside the integration. It is just r square dr. Limits. The first mass is here when r is 0. The last mass is here when the value of r is L. So 0 to L. That's why the limits. So m by L, r squares integration, r raised to 3, whole thing divided by 3. Obviously the limits 0 to L. So m by L, first put L cube by 3 minus 0 cube by 3. Anything minus 0 is anything. So L cubes L will cancel. I will be left with L square. So ml square by 3. That is the moment of inertia of that particular rod about the end, at the end of it. I hope this is absolutely clear. So this is how the integration is performed. Now, you will be wondering, sir, do I have to do this integration for all the things? No. You should have an idea how it is done. That's enough. They won't ask you derivations, obviously. Now it's an objective exam. So you should just remember the formulas. That is more important. Okay. So we'll come to the formulas. Okay. And what are those formulas for all the simple geometries that you have? First of all, the moment of inertia of a ring. Then you have moment of inertia of a disk. Moment of inertia of a ring. Moment of inertia of a disk. Then you have moment of inertia of a hollow sphere. Moment of inertia of a solid sphere. And lastly, the moment of inertia of a rod. Now, guys, very straightforward. Moment of inertia of a ring is nothing but mr square. Moment of inertia of a disk is mr square by 2. Moment of inertia of a hollow sphere is 2 by 3 mr square. Moment of inertia of a solid sphere is 2/5 of that mass into the radius square. And moment of inertia of the rod is nothing but ml square by 12. Now I know you will be like, sir, you just found out that it is ml square by 3. How come you are writing ml square by 12? I'll tell you why. Because the axis is the central axis. This axis was at the end. So when you measure it about the center, that means you take a rod and rotate it like this. Not rotate it about its end. No, but you take it over here and then rotate it about its center. Then the formula will not be ml square by 3, it is ml square by 12. So it's very important that you know about which axis each of this body is being rotated. So first of all, let me just show all the bodies over here. This is so what is the axis in every case? So let me just put it up over here. This is the axis, mind it. This is the axis. This is, all the axes are central axis, mind it. Okay, all the axes are going to be central axis. Is this absolutely clear, guys? Everyone? So these are the formulas which you must know. Very, very critical. Yeah. So the moment of inertia in case of a solid sphere, 2 by 5. For hollow, 2/3. 2/3 is like 66%, roughly, give or take. 2/5, guys, is like 40% of mr square. This is 40%. This is 66%. So why is it more here? Why is it less here? Simple fact, in case of solid, some people think, sir, more mass. No, don't take more mass because you have to keep the mass same, radius same. But for solid sphere, the masses are more closer towards the axis. In hollow, the masses are far away on the periphery. As you go far away, distribution increases, R increases, moment of inertia increases. Solid, the masses have to be distributed everywhere. So some of them end up coming close. In fact, some of them will also lie on the axis whose distances will be 0. That's why it becomes lesser than the hollow sphere. I hope this is absolutely clear. Yeah, it's going to be a long class. Expect bare minimum. We are going to cross 12 o'clock for sure, guys. Okay, 100%. Let me tell you that. Okay, now there is a very interesting thing which you should know. Imagine there is a two-dimensional thing which is given to you. This is a 2D lamina. Lamina means like a sheet. And somebody hypothetically pulls it down. Somebody hypothetically, oops. Okay, not the same exactly, but I will try to draw my best. Somebody tries to pull it down, something like this, and now it becomes a three-dimensional object. Now it has become basically a three-dimensional object, something like this. From 2D, it has become 3D. Since you have nothing but stretched it, you have stretched it. The mass hasn't changed. Check this out. What and all hasn't changed. Mass is going to be the same, definitely. What about the axis? Well, axis is also same. Let's say it was rotating about this particular axis. Now also it is being rotated about that same particular axis. The axis also hasn't changed. Same axis. So axis is also going to be the same. A mass here is just being stretched. So the distance from the axis hasn't changed. A mass here, if it was here, that same mass is now being pulled like this. All the masses are at the same distance. So guys, understand, neither has the distribution. The distribution of the masses is also going to be the same. What does this tell you? It just tells you all the three factors which affected the moment of inertia, which I have been telling you before also. mass, distribution and axis. They all decide the moment of inertia. None of them have changed. So why should the moment of inertia change? So hence, I will say that the moment of inertia, therefore, the moment of inertia is going to be the same. This is very, very important. The moment of inertia is going to be the same. So if this had some formula for moment of inertia, let's say this was I1, let's say this is I2, this I2 will be equal to I1. That's it. Both of them will be the same. You know what is the best part about this? Let's go back. What happens if somebody pulls a ring? What happens if somebody ends up pulling a ring-like structure into three-dimensional structure? What will it look like? Can anybody guess? If somebody pulls a ring into basically something like this, what does it look like? It looks like a hollow cylinder. Hence, the moment of inertia of a ring and the moment of inertia of a hollow cylinder is exactly the same. This is also going to be equal to mr square. There is no difference at all. Is this absolutely clear? Yes, but it is a hollow cylinder. Same way, if I end up pulling a disc, like this, what is it going to become? A disc. There are masses even in between somewhere. Yes, there are masses even over here, guys. There are masses even over here. Everywhere there are masses. So it's completely full. So it is going to be a solid cylinder. So this is the moment of inertia of a solid cylinder. It is definitely going to be the same, and it will be mass radius square divided by 2 only. No difference at all. Is this absolutely clear? Just from the stretching property. Very, very important. The property is the stretching property. You stretch anything along that same axis, the moment of inertia remains the same. Okay, very important. Let's go ahead. Yes, you can't do that with solid sphere or hollow sphere, because hollow, if I stretch it, it looks very weird. Imagine it solid sphere. I can't really stretch. I have to put so many solid circles. There will be so many overlappings. It will not be a physical structure in reality. It will be very weird. Yeah, can we derive the moment of inertias of these things? Yes, it is there in many books like H.C. Verma and other things, but no need. You should just know that it is again done by the same process what we have done over here. So for a disc, you make it into multiple rings. For hollow sphere, the rings are being added together to make it hollow. Small, big ring. So you take many hollow spheres, concentric, like an onion, then it becomes a solid sphere. So the derivations are dependent on each other. Great. Till this point, I hope it is absolutely clear. So let's see if you guys can figure this out. Very interesting question. If a disc of aluminium, these days on the reels, there is one lady who is called as the aluminum lady. Very interesting lady. She sells houses. I don't know how many of you have checked out the reels and the shots. Okay. So the way she says aluminium is very, very fancy. If a disc of aluminium is having a moment of inertia of I, then a disc of aluminium of double the radius is question mark. How many times of that old moment of inertia? Come on. Yes. Okay guys, concentrate on the class. Other questions later on, maybe in the comments. Concentrate, because it's going to be a long class. I cannot deviate from the class too much. If it's a 1-2 hours class, fine, but this is going to be a really, really long class. Yes, so what is it going to be? Let's find out. Because the material is the same, because aluminum, that means what is going to be the same? It's the density which is going to be the same. Density is going to be the same, but which density? It's a disk. A disk is a flat object, sheet-like object. So the quantity which you should refer to is mass per unit area. So this is going to be areal density. Areal density is going to be the same. Now, as per this, sigma will be the same. If the original mass is m, radius is r, so mass per unit area will be mass by pi r square. Second time, I don't know what the mass is, so I'll just put it as m1. The radius is double, so 2r square. So what will happen now? Pi cancels. M by r square will be m1 by 4r square. R square also cancels. So m1 will become 4 times of the mass. So the mass has become 4 times. The mass will be different. Be careful of it. Oh, so if the old moment of inertia was mr square by 2, the new moment of inertia will be the new mass, which is 4m, the new radius, which is 2r whole square divided by 2. 4 and 2 square. 2 square is basically 4. 4 4s are 16. Correct? I hope this is absolutely clear. And we have mr square. This 2 is as it is. This particular 2 is as it is. So mass has been made 4 times. Distance, radius has been made double. So 2 square is 4. 4 4s are 16. But what is this mr square by 2? It is nothing but your old moment of inertia. Hence, the new moment of inertia becomes 16 times the old inertia just because you made the radius double. Yeah. So you can do that for any other object as well. You can stretch a rod. Okay, you can stretch a rod. Oh, by the way, this was not stretching. This was a new disk. If you stretch a rod or something like that, the mass might be same. The distance will increase. That's it. L will change. Mass will be same. So when you stretch something, mass is same. But this is not stretching in this case. This is basically a new disk of the same material but of a different radius. I hope this is absolutely clear. Okay, beautiful question. Let's go ahead to the next one. The next question is, if a wheel like a disc, or let's do one thing, if a solid ball of 2 kg and 50 centimeter radius spins at 50, or let's say 20 pi radians per second, find its rotational kinetic energy. Find its rotational kinetic energy. Let's see if you can figure this bit out. To find the rotational kinetic energy, I think I had given one formula just some time back. The rotational kinetic energy is half I omega square. Okay, so I just need to find moment of inertia. All right, and then my job is done. Okay, so what is the moment of inertia of a solid ball? It is 2 by 5 because it's a solid sphere. For solid sphere, I just told you it is 2 by 5 mr square. Okay, so it is 2 by 5 m into r square. And kinetic energy is half I omega square. So put I is nothing but 2 by 5 mr square, and then we have omega square, 2 cancels. So mr square omega square divided by 5 is the kinetic energy. So start putting the values now, we will get the answer. What is the mass? Mass is 2 kg. What is the distance? Radius. The radius is 50 centimeter, so which is like half meter square. What is omega? It is basically 20 pi and you square it. The whole thing is divided by basically 5. Okay, let's see what happens. This is 2. Okay, the 5 is there. Okay, multiplied by 1 is there. 2 square is 4. 20 square is 400. Pi square is as it is over here. 4 goes with 400. You can see that very clearly. 100 times. Now, listen to me carefully. Pi square is as good as saying it is 10. Pi square is as good as saying it is 10. 5 goes with 10 2 times. So the final answer will be 2 2s are 4. 4 into 100, approximately, this will be 400 joules. That's the rotational kinetic energy. Is this absolutely very clear, my dear warriors? Yes. Is this understood? Is this understood? Yes. Very, very clear. Yeah. Perfect. Perfect. Yes, the answer is 400 joules. Very good, guys. Awesomeness. Awesomeness. Let's move ahead to the next. Let's move ahead to the next question. Can we apply energy conservation in some problems? You might be wondering. Yes, you definitely can apply conservation of energy also in many problems. You'll be wondering, is it so? Really? Let's try it out. How about this particular question? Just imagine there is a pulley. There is a pulley like this over here. It is attached to the roof. Let's say the mass of the pulley is m. The radius of the pulley is basically r. There is a thread wound over it. And there is a point mass over here. Let's say this mass is 2m. This mass is m. Right now, it is at rest and it is now left from rest. After some time, what happens? This mass is going to fall down by some height. And by the time it falls down over here, this mass will have some velocity. Question is, how much is this velocity going to be? How much is this velocity going to be? That's the question. Now let's try to visualize what exactly might be happening over here. Okay. When this mass falls down by some particular height and this mass comes over here, when it has some velocity, do you think this pulley, which is having some mass and the thread is wound over it, do you think it will stay quiet? Do you think it will stay quiet? Obviously, it will not stay quiet. Obviously, it will start rotating. So when this is going down with speed v, don't you believe that this pulley will also have some angular velocity, guys? Definitely, it will have some angular velocity. Now, if this is clear, are these two going to be related to each other? Will this v be related to omega? Think logically, guys. It will be, in fact, because if you look at the pulley, all the points on the circumference will be going like this, like this, like this, like this. And the same point will continue over here in that thread going like this. V, 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 V. And what is V? V is nothing but it will have some angular velocity. So it will be omega into r. So 100% V is related to omega. That is also clear. Oh, okay. Now let's think. When this mass comes down, what is it losing? What is it exactly losing? Think about it. Yes, it's loss of gravitational potential energy. Whom? In that particular mass m. Where is it going? This mass lost gravitational energy. Where did it convert into? Even this mass got kinetic energy. So kinetic energy of that mass m. Not just that, this pulley also started spinning. So, and the kinetic energy of that particular pulley of mass 2m. Of mass basically 2m. I hope you understand this. As this mass comes down, it loses gravitational energy and it converts into rotational energy of the pulley, or else where else will it get that energy from? Think about it. Because this mass came down, the tension passed on that energy. Perfect? Yeah. Yeah, the speed will keep on changing, But at every instant, whatever that new speed is, that will be related to that point omega by omega r. So omega will also keep changing. First the wheel will spin slowly, then it will be fast and faster as it unwinds the thread which is wrapped over it. 100% omega will change. Oh, so what is the loss of gravitational potential energy, guys? Won't it be mg into h? Okay. What is the kinetic energy of that mass? It is translating, so half mv square. Kinetic energy of the pulley, it will be half I omega square. Why? Because it is rotating, not translating. That is the catch. A lot of people write half mv square here. So therefore, mgh is equal to half mv square plus, what is the moment of inertia of this pulley? It's like a disc. So it is mass into radius square, whole thing divided by 2. That's moment of inertia. And what is omega? Omega will be v by r. V by r, and that is squared. Omega is velocity by r. Perfect. So what is this term becoming? 2 cancelled. R square cancelled. So only 1/2 is remaining. M was remaining and only v square is remaining. 2 got cancelled. This half mv square is there and mgh is also there. M cancels. So gh will be v square by 2 plus v square by 2, which is just v square. So v will be root of gh. That is the answer. Speed is root of gh. Is this absolutely clear, my dear warriors? Understood? Yeah. So this particular mask which is there, this pulley, we can take it like a disc because pulley is solid. It's not usually a rim. It's a solid pulley. So it's like a disc. So that's why mr square by 2. Cool. If till this point everything is understood, can we go ahead? If till this point everything is understood, can we go ahead? Yeah. Let's go ahead. Let's go ahead. Perfect. Let's go ahead. Now we have found out moment of inertia of all the simple geometries which are there in our syllabus, be it a ring, be it a solid cylinder, be it a hollow cylinder, all these things. Okay, we can try some more geometries also by using some properties and some theorem. Let's see first of them. The first of them, very interesting. One very interesting variation which comes is this one. They give you a sector of a circle and they tell you, listen, this is, you know what, let's say for example 20 degrees and this mass is m, this radius is r, and the axis of rotation is right over here. Question is, find the moment of inertia. Find the moment of inertia. That's what the question is. It's like a slice of a pizza and they tell you find the moment of inertia. Whenever such problems come, don't break your head so much. The answer is going to be same as what would you get if you complete the diagram and the formula which is there for that complete diagram. For example, if you have a slice of a pizza, if you keep adding more such slices, what you get is basically a disc. What you get is basically a disc, and this is just one slice of it. Maybe I'll just shade it over here. Yeah. So what you get by adding those slices is basically a disc. Similarly, if it was an arc, if you keep adding all such arcs, what you get is a ring. Is that making sense? So what is the moment of inertia formula for a disc? It is nothing but mr square by 2. So the answer for this, irrespective of this angle, will also be mr square by 2. Yeah, the mass which I am considering is only of this part, not the whole thing. And there is a very easy way to do this. I'll tell you how. Imagine if the moment of inertia of that one slice is I, if let's say there are n number of parts, if I keep adding them, n times of I will be the moment of inertia of that complete disk. This guy, if I add them, I should get the moment of inertia of the entire disk. Everybody agrees this? Okay. So what is the moment of inertia of the complete disk? Well, it is the total mass of that particular disk multiplied by r square, whole thing divided by 2. What's the mass of the disk? Well, each sector had mass m. Each sector had mass m, correct? So there are n such sectors. So the total mass will be m into n into r square, whole thing divided by 2. This is n times of I. N will cancel. What is the formula? It is m r square divided by 2. This mass is of a sector, radius anything, and this is the moment of inertia of that sector. So the formula won't change, hence the answer is still the same. So guys, the answer to this question is just mr square by 2. Whether it is 20, 25, 30, 60, 100, really doesn't matter for a slice of something. Yeah? Yeah. I hope this is very, very clear. Yes. So we are not considering something else like the edge of the disk, the chord of a disk and all such things. We are just considering basically the entire disk as a whole, or the slice includes the interior parts including the rim. Okay, I hope this is clear. Great guys. Now the next property is called as, very important thing, is called as a parallel axis theorem. Parallel axis theorem, which says that if you have some body, okay, and let's say the center of mass is somewhere over here. Let's say the center of mass of that body is somewhere here, and there is some axis maybe which passes through the center of mass, and the moment of inertia is ICOM about that axis. You want to find the moment of inertia about some other axis which is parallel to it. I don't know what that moment of inertia is. Let's say I call it I, and the distance of this axis from this axis, the distance of this particular axis from this axis, that distance happens to be d. That happens to be d. Then the moment of inertia about this parallel axis. That's why the name parallel axis theorem. These two axes are parallel. One of them is through the center of mass. The answer to that is the moment of inertia about the center of mass plus you take the entire mass of that object and write d square in front of it, the distance between those axes. So square it. That is the answer. This is called as the parallel axis theorem. This is called as the parallel axis theorem. Necessarily one of the axes should pass through the center of mass. This also tells me one interesting thing. If I had multiple such axis options available, because every time this term will never change, only the d will change. Of all these axes, the d will be the least if the axis passes through the center of mass, which means this extra term will be there if I am anywhere apart from the center of mass. So the moment of inertia will be the least when the axis passes through the center of mass. Very, very important. So a very important property which I can see, of all the parallel axis, the moment of inertia is the least. Of all the parallel axis, the moment of inertia is the least when it passes through what? The center of mass. When it passes through basically the center of mass. Very, very important property. We can put this property to a test for a rod basically. Let's take a simple solved example. Remember when I did the derivation for this end, and I told you the moment of inertia about this end, we just figured it out by derivation. If you remember this correctly, where did it go? Yeah, over here. About the end was ml square by 3. It was basically ml square by 3. So this I was nothing but ml square by 3. Let's say I wanted to find the moment of inertia about the center of that rod, and obviously it passes through the center of mass. So if I want to find the moment of inertia about the center of mass, what should I do? I know that this particular I is actually a parallel axis. This will be equal to I center of mass plus what's the distance of this point to this point? This distance is L by 2. This is L, L by 2, L by 2. So basically plus M into L by 2 whole square. Using nothing but parallel axis theorem, nothing else. Parallel axis theorem. So let's start substituting values. I is nothing but ml square by 3 is equal to, this is I center of mass plus you have ml square by 4. So what will I center of mass become? It will be, you have ml square by 3, ml square by 4. So ml square is common, 1 by 3 minus 1 by 4. So ml square is here, 3 4s are 12, 4 minus 3. 4 minus 3 is 1. So ml square by 12. That is the moment of inertia about the center of mass. Exactly what I gave you in the table. Exactly what I gave you in the table. ml square by 12 about the central axis. If you go towards the end, then it is ml square by 3. Is this absolutely clear how we use this theorem? How we have used this theorem, guys? Let's go to one more example and see how to get the answer. Let's say, for example, oops. The difference is, this is a ring, this is a disc. Where is the axis? The axis is at the end, passing through the periphery, the circumference. It is perpendicular to the plane of that figure. Question is, find the moment of inertia. Obviously, in order to find the moment of inertia, we need some another axis because it's not your regular axis. The axis which I know the moment of inertia about is the axis which passes actually through the center of mass. And in this case, this axis has a moment of inertia of mr square. This has moment of inertia of mr square by 2. So if I add to it this distance, which is basically r, so m distance square. Here again this distance is basically r, so mass of the body into r square. I should get the moment of inertia about the required axis. So the moment of inertia in this case, mr square plus mr square, 2mr square. Here mr square plus half mr square, 3 by 2 mr square. That is the answer. Is this clear how to use this? It's not exactly a tangent, but it is perpendicular to the plane of the figure. So if it is a ring, imagine if it's like a ring over here, it is like this. It is not in the plane of the ring. It is not like this. It is perpendicular to the plane of the ring, okay, or the disc. Be careful. Amazingo, clearo, perfecto. Shall we go ahead? Oh, amazing. Let's go then. Let's go. So this was the next important thing which we learned. Now we have one more amazing thing which helps us find the moment of inertia. Like we have parallel, we have perpendicular axis theorem. Perpendicular axis theorem. Like the name suggests, something will be perpendicular. But there is a catch over here, and the catch is it's only for laminar bodies, laminar or sheets like body. Only for 2D objects, ring, disc, square plate, triangular sheet, a cutout of a sheet, valid. Sphere, cone, cylinder, not valid. Bent figures, no, not valid. Okay, only for laminar bodies. So say for example, this is our laminar body. This is our laminar body. Like the name suggests, perpendicular, so we need to have perpendicular things over here. So the first axis is like this in the plane. Second axis is also in the plane. Need not pass through the center of mass or anything. It could be anywhere, guys. So don't get confused and think that it should be the center of mass. So these are the two axes which are in the plane. So I will call this as, let's say, I1, and this is basically I2. So I1 and I2 are basically the moment of inertia about the axis in the plane. You take another axis which is perpendicular to the body but necessarily should pass through the intersection point. This is our perpendicular axis. So I perpendicular is nothing but the moment of inertia about a perpendicular axis to the body. Then this I perpendicular, simply put, is nothing but I1 plus I2, nothing more. Just I1 plus I2 is the total moment of inertia. That's it. I1 is the moment of inertia when you rotate the body like this. I2 is the moment of inertia when you rotate it like this. I perpendicular is when you rotate it like this. So this perpendicular is just I1 plus I2. That's all it says. Very straightforward. Very straightforward. Concentrate on the class. Don't worry if anybody spams. Yes. Yeah. Is this absolutely clear, everyone? Awesome. Awesome. Excellento. Amazingo. Great. Let's put this formula for a test for some geometry. Let's say we take the example of a ring again, or a disc or something. Remember, it's only valid for two-dimensional geometries, and we have to find the moment of inertia about this particular axis. Okay, that's the question. Question is to find the moment of inertia about this particular axis. So what I will do? Usually I don't know about this axis, but what I know, I will draw first. I know about this axis. But the thing with this axis is it is perpendicular to the plane of the figure. So actually this becomes I perpendicular. And what I want to find is an unknown. And this I perpendicular, I know it is just mr square. It's like a ring, right? Because it is a ring. So definitely it is just mr square. Okay. What then? I need, for applying perpendicular axis theorem, I need 1, 2, 3. 3 axes. All 3 are perpendicular to each other. In the question solution, I just have 2. I need 1 more. So why not draw an additional axis which is in the plane like this? Best part, if this is the diameter, even this is the diameter. In fact, there are so many diameters. So guys, if this has inertia I, even this will have that same inertia I only. There is no difference at all. Is that obvious or not? So hence this should be equal to I plus I, which means it should be equal to 2I. Therefore, I will be mr square by 2. It is nothing but mr square by 2. Is this clear, everyone? Yes. Why only 2D geometries? It's because the way it is derived. So when the derivation is understood, then you will understand why only for 2D it doesn't work for 3D. So it comes in the derivation. Okay. So there are some assumptions which you do, and you will see the moment it is 3D, something extra term will come, and that's why it fails for 3D geometries. So it won't be just I1 plus I2. It will be I1 plus I2 plus some complicated integration. So we keep it simple for 2D geometries only. Let's take another example, guys, a very beautiful example. Now this is a disc, but notice where the axis is. It is basically tangential over here, and you have to find the moment of inertia. You have to find basically the moment of inertia, and it's a disc. Now you'll be like, okay, this is slightly weird. What do we do now? Don't worry, you have to do it in multiple steps. What do you know? You first draw. Whatever you know, right? You first draw it. I know the moment of inertia about this axis. Okay, so I will draw this one first. Okay, so moment of inertia is known for only this axis. How much is that moment of inertia? That also I will draw. That moment of inertia, because it's a disk, it is mr square by 2. How do I find it about the tangent in that same plane? So if it's a disk, the axis is tangential in the same plane. I need to do one thing though. I need to know what is the moment of inertia about this axis. These two are parallel. Think about it. These two are parallel, and this axis, the blue one, is the axis which is passing through the center of mass. So it is actually ICOM. Don't you see that? It is passing through the center of mass. You shift it, you get the required moment of inertia about this axis. The problem is, what is this ICOM? That also I don't know. No issues. You draw one more ICOM. You draw one more ICOM like this. See if you are able to visualize this, guys. An axis which passes through the center of mass, but over here. This also is ICOM. Oh, this, and this, the green and the two light blues are perpendicular. It's a two-dimensional geometry. So hence, using perpendicular axis theorem, what do you get? ICOM plus ICOM, which are both in the plane of the figure, will be equal to the moment of inertia in that perpendicular direction, which is mr square by 2. So this will become 2 times of ICOM. So ICOM will become mr square by 4. 2 2s are 4. That is what we get. Correct? But we don't stop there. We have to shift it to this point. We have to shift it to this axis. So which theorem will we use? We'll definitely use the parallel axis theorem. The parallel axis theorem. So how much are we shifting it by? This distance, which is r. So the required inertia will be this guy, ICOM plus m into d square. ICOM is mr square by 4. Distance of shift is just r. So 1 by 4 plus 1, 1 by 4 plus 1 is 5 by 4. So 5 by 4 mr square is the moment of inertia. That is the correct answer. Is this absolutely clear, my dear students? Understood how this question was to be done? Perfecto. Perfecto. Okay, amazing. I have a very interesting thing to show you now, to combine some theorems and get one interesting geometry. See, if I have a rod and I rotate it about the central axis like this, and the rod's mass is m, length is l, the moment of inertia about this axis is nothing but m l square. It's a rod, so by 12. What if I stretch a rod? What if basically I stretch that rod? What will it look like? Obviously the rod will stretch to become a sheet. It will stretch to become basically a sheet. So now this rod has been converted into, this was a rod, it has now been converted into a sheet. And this is the axis of rotation. This is the axis of rotation. Okay, fair enough. The moment of inertia will be the same, because that's what I have told you. When you stretch anything, the moment of inertia wouldn't change. Now please mind it that this is L and the height or the breadth could be, let's say, B. So if this is L, this is B. What, by the same logic, had I rotated or had I spinned it about some another axis, but it is like this? If it is like this, what do you think the moment of inertia would be about this particular axis? Instead of this axis, when I spin here, ml square by 12. When I spin like this distance will matter. So it should be m, what should it be? M, yes, perfect, mb square by 12. Everybody agrees with this point? mb square by 12. Very good. It's a sheet. Now let me visualize that sheet in 3D. That will be better. This is our sheet. Let's say this is our sheet. This is length L. This is breadth B. This was one axis. This was another axis. Wow, it's a laminar object. I can already see two axes over here. So if this is M B square by 12 and this is M L square by 12, I draw a perpendicular axis now to both of them, something like this. What should be the moment of inertia, guys? Quickly think and tell me. The addition of these two by perpendicular axis theorem will be nothing but M by 12 L square plus B square. So about the center of mass, perpendicular, if you rotate it like this, M L square plus B square. Now I have one more weird idea, that what if I end up stretching even that sheet to make it look like a cuboid. To make it look like a cuboid. Wow. So from a sheet, we have gone to a cuboid whose length is L, breadth is B, height is H. And this is the axis, guys. Crazy. Passing through the center. The moment of inertia will be the same. So using simple properties, I can find the moment of inertia of a cuboid, which is just ml square plus b square, whole thing divided by 12. Isn't it amazing, guys? How we went from a rod to a sheet to perpendicular axis theorem to stretching it to make it a cuboid. It's a beautiful, beautiful concept. Isn't it? Loved it? Awesome. So if you do not feel wow after looking at this problem, something must be seriously wrong. Okay? So quickly smash the like button in case you haven't done that yet. Yeah? Quickly smash the like button. Okay, great. Now, there is a small thing which you should know, which is called radius of gyration, very laddu thing, but still I will tell you about it. So guys, radius of gyration. This gyration means something associated with rotation. So say for example, we have some big body, okay, some random body, and it is rotating about some axis. Let's say this is our axis. And I want to know how far or close the distribution is. I'm not interested in the mass, but I'm interested in what is the average distribution like. Is it close? Is it far? That's all I'm interested in. So when this body is rotating about this particular axis, mass is, let's say, m, the moment of inertia is I. It depends whether it's a solid, hollow, sphere, cone, whatever. Solid sphere, it is 2 by 5 mr square, ring, it is mr square. So I will depend on the mass and the dimensions and the geometry shape. But if I convert this entire body into a singular point mass, same mass, then whatever distance I need to keep so that the moment of inertia is the same as before. This is the moment of inertia of that body. Here I have melted it into a point mass. I should be the same. Then that distance at which you keep it is given a symbol k. That is called as radius of gyration. So radius of gyration is that distance from the axis where the entire mass can be assumed to be concentrated so that it has the same moment of inertia. So I'll write it down over here. Radius of gyration is the distance from the axis where the entire mass can be concentrated such that it has the same moment of inertia as the original or the body before. So the moment of inertia formula for a point mass, we already know it is m into distance square, so mk square. So I body will be mk square. So this formula helps me find k. This formula basically helps me find the value of k, nothing more, nothing less. Let's do a question, then you will understand it. Let's do a question so that you get an idea of it. For example, if the question says find the radius of gyration of a hollow sphere, if that is the question, what will you do? You will say, okay, whatever is the radius, moment of inertia of a hollow sphere, this body should be mk square, should be equal to m into radius of gyration square. The moment of inertia of a hollow sphere is 2 by 3 mr square. 2 by 3 mr square. Cancels, so k square will be 2 by 3 r square. So take the square root on both sides, so r root 2 by 3. So it has nothing got to do with the mass. It just tells me how far should we keep that point mass so that it behaves like the original body, moment of inertia wise. Very straightforward. Okay, let's do one last question on this. If a question says the radius of gyration of a wheel is 2 meters, and mass is 10 kg, find the moment of inertia of that wheel. Very straightforward. Find the moment of inertia of the wheel. As per the definition, I want to find the moment of inertia of the wheel. Mass is given, radius is given of gyration. So straightforward, guys. Answer will be the moment of inertia of that particular wheel will be mass of the wheel into k square. Mass of the wheel is 10 kg. Radius of gyration 2, so 2 square. 2 square is 4, 4 into 10, 40. So 40 kg meter square is the moment of inertia of that particular wheel. Very simple. Is this clear how to do this? Yes. Okay. Any other question on other things? We will do it later on. Okay. Don't worry. Yeah. Yes. Thank you for reminding me for having water. Root mean square and all that, don't go by that. So even though the formula might look to be something else, no, don't define it as root mean square and all. Though it might be defined in some other ways, don't worry. Physics wise, it is defined as the point where you should melt that body to be kept as a point mass so that it behaves like the original body to produce same moment of inertia. Yep. I hope this is absolutely clear. Perfecto, perfecto. Great. So, till now, if you notice, we have, where is it? Yeah, we have studied, okay, the equivalent of mass but in rotation is I, and the kinetic energy but in rotation, instead of half mv square, it is half I omega square. Just like we applied energy conservation here, we can also apply energy conservation here. Okay, so we have understood how to find the moment of inertia of a body. If it is a discrete mass system, you add each moment of inertia separately. If it is, a continuous mass, then you have to integrate. But usually we don't integrate because most of the times we know the standard formulas. But if the axis is not at a standard place, then we use some properties. Like if you stretch, the moment of inertia is same. Or for that matter, if it's a slice of something, you add more slices, whatever geometry you get, the same formula remains, but provided this mass is the mass of this slice over here. And then you also saw parallel axis theorem. So you have parallel axis. If you know the center of mass's moment of inertia, you shift it by some distance d. And the last one we saw is for the perpendicular axis theorem two of the axes must be in the plane. The third one is perpendicular to that plane. So that's how you can find it out. And we did some combination questions. So that's about moment of inertia. Now let's go to the next quantity. What is that next quantity? Well, that next quantity is basically angular momentum, guys. Yes. Ready for it? Angular momentum. Just like we have linear momentum P, which is m into v, we have angular momentum. We have angular momentum. Now, before going there, let me just ask you one simple thing. If a body is rotating and translating both, then the total kinetic energy of the body is the sum. What will be the sum of? Number one is the sum of kinetic energy of the translation of the center of mass. So if a body is, just imagine this, guys. Right now, if this is the body, this is pure rotation. If it just goes like this, like this, like this, it's translation. Now just imagine it is rotating while it is translating. Just like how Earth goes around the sun, it is rotating plus translating, right? So you assume the entire thing to be a point mass. Where will it be a point mass? At the center of mass. So it will be the translational kinetic energy of the center of mass. That means you assume the Earth to be a point mass and then it is translating. So half mv cm square or half mv square. That is what we are talking about over here. Kinetic energy of the translation of center of mass and is the sum of, very important, and the kinetic energy of rotation about the center of mass. Meaning you assume the Earth to be a point mass, translational energy will be half mv square, and about the center of mass, if you sit, let's say this is the axis, you sit on the center of mass, what will you see? You will just see the Earth spinning, rotating. So the rotational energy as seen from the center of mass. So very important, many people remember this as, sir, it is rotational energy plus translational energy. Wrong. It's not any random points translational energy. Because when the Earth is going around the sun, there are so many different points, so many different speeds. Which speed will you take? It is the speed of the center of mass. It's the speed of the center of mass. Very, very important, guys. So therefore, the kinetic energy of any random body will be the sum of two things. Kinetic energy of the center of mass, which I can write it as half mass of the body, velocity of the center of mass whole square, plus half moment of inertia about the center of mass. So half ICOM omega square. So this is the formula, guys. This is the formula. Very, very crucial. So let me just draw a random body over here and let me mark some things. Okay, so this is the center of mass. So this is velocity of the center of mass. About the center of mass, when it rotates, it will have some angular velocity, and about the center of mass also, it will have some moment of inertia. So you add them both, you will get the total kinetic energy of that particular body. Is this absolutely clear, everyone? Is this absolutely clear, everybody? With me on this? Perfect. Yeah. So mainly in circular motion and rotational motion, what's the main difference is, in the circular motion, we never worried about the dimensions of the body. We always treated the bus, car, bike or anything as a point mass, and we just showed the FBD of a point mass. Here, you are worried, is the body a ring? Is it a solid sphere? All those things. So that's the major difference. It's a collection of bodies that we are studying, not a single point object. So that's what you study in rotation, a collection of bodies. And you are also understanding what happens when it translates plus rotates in most of the cases. That's one major difference, guys. Okay, absolutely clear. Let's understand it with an example. So say it is a rod like this, and I tell you that, hey, listen, there is this midpoint which is going with some speed, and this end point is going with some different speed. This is V, this is basically 3V. Question is, find the kinetic energy of the rod. Okay, question is, find the kinetic energy of the rod. At first you might think, sir, this will be a very easy problem, but trust me, there is a lot of things to it. Okay, first, it is given to me the length of the rod is basically L. The length of the rod, okay, is basically L. That is what is given to me. Now, I will first of all realize that, okay, this velocity is at the center. So strictly speaking, since this is the center of mass, this velocity is actually the velocity of center of mass. And that is what I will need also. I will need half m velocity of center of mass. So first part is at least done. Main thing is remaining, which is omega, angular speed. So for that, I will visualize a little bit. I'll just visualize a little bit. Just observe this carefully. If you sit on the center of mass itself, so basically you are talking from the center of mass frame. You will see that the body, because this point is moving slowly, this point is moving fast, obviously the rod is spinning. It's not only just translating, but it is also rotating. There is rotation plus translation. How many of you are able to visualize this? It's not just going like this. This is moving slowly, this is moving fast, so it is actually going like this. Everybody, till this point clear? Okay, awesome. Ashwin, I'll reply to you later on. Yeah, we'll have a break after some time. Yeah. So there is definitely some angular velocity. How much is that? We'll come to that. Okay, this point has a speed v, this point has a speed 3v. So in the relative frame, what might be the speed? Relative velocity of this point with respect to this point. Quickly put the answer in the chat box. Guys. Come on. Yes. Same direction the speed. Same means put your hands like this. Bring them together. Looks like a minus sign. So that means you have to subtract 3v minus v. Exactly. So it will be 3v minus v, which is basically 2v speed. Okay. Not just that. This distance is L by 2. This is velocity, this is radius, this is omega. So velocity is r multiplied by omega. Use this. So velocity is 2v. R is nothing but L by 2. Omega, I don't know. So how much will omega be? It will be 4v divided by L. Is that right? So we got omega also. Yes. So definitely we can find now the kinetic energy of the rod, which by formula is half mv center of mass square, which in this case is half m. Velocity of center of mass is just v only, plus half I center of mass omega square. Moment of inertia of the rod about the center is ml square by 12. Omega, we just got it, 4v by L, and this is square. Okay, so what do I get? 4 square is 16, 16 by 2 is 8, so 8 by 12, m, L square cancels, so v square, 8 goes with 4 2 times, 12 goes with 4 3 times, and this mv square by 2 is anyways remaining. So what is the final answer that I get? This is 1 by 2, this is 2 by 3. Just check this out. 4 square was 16, 16 by 2 was 8, so 8 by 12, so 2 by 3, perfect, and this is mv square. Everything fine till this point? Okay, L square just got cancelled, only V square is remaining. So 1 by 2 plus 2 by 3, guys, 3. So that will be nothing but 3 plus, 3 plus 4. Yes, 3 plus 4 by 6 mv square. So that is nothing but 7 by 6 mv square. That is the answer. 7 by 6 mv square. Is that right, everyone? Got it? Clearo, 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 perfecto. Shall we go ahead? Shall we go ahead? Yes. Clear till this point? Great. So this is how you can solve these questions which are related to translation as well as rotation both. Very few times such questions come, but in case they come, this is what you will do. So now coming to the next point, which is basically angular momentum. Angular momentum is basically equivalent of momentum in rotation. That's it. Just like you have momentum, you have angular momentum. The symbol is L, capital L, not small l, capital L is the symbol for angular momentum. So what is the angular momentum of a body? Well, there are two different cases, and in both the cases I will tell you what the answer is. First case, this is our axis. Okay, so yeah, this is for a point mass, very, very important. This is for a point mass, This is for a rigid body. It's a continuous body. Just like we had continuous body and point masses, same difference, guys. If it's only a particle, a ball is being thrown like a particle. But if it's like a big stone rotating about its axis or a big ball rotating about its axis, then it will be this consideration. In this case, the angular momentum formula versus over here, the angular momentum formula is as follows. Here it is mass of the body, distance from the axis, which is now called as a position vector. It's the position of the body from the axis. Cross product it with the velocity of the body. So m r cross v, that's for a point mass. But if it is a rotating body, then it is just moment of inertia of the body into angular velocity of the body. That's it, I omega. Now there is a very interesting thing which you will see. You will be like, sir, this I omega, can you give me some feeling for it? Yes, I will give you the feeling for it. Let me just go back over here where we compared everything. And let me just write down over here momentum. Let me just write down over here momentum. What was the formula for momentum? Was it not mass into velocity? Was it not mass into velocity? So when I want to write angular momentum, symbol is S. Instead of mass, what should I write? I. Instead of velocity, what should I write? Omega. Perfect, matches exactly. So guys, there is lot of similarity. It is like same but different. Same but different. Mass into velocity, moment of inertia into angular velocity. That gives you angular momentum. So guys, very straightforward looking formulas, guys. Nothing difficult as such. If you remember linear motion, you automatically can remember rigid body motion. Is that right? And remember, usually I, for a point mass, if it is a point mass, it will be mr square. Omega will be v by r cancels. So what will you get? mrv. So, you can see actually they are all dependent on each other. It's not like they are coming from magic. Yeah. So I hope you guys can see that for a point mass, you can just write this as mr square, omega is v by r just cancelled, it became mrv, right? So, and that cross product comes because of the directional aspect of it. So now over here, if you see, the position vector is here, velocity vector is here. If I put the fingers of my right hand in the direction of r, slowly curl it towards velocity, angular momentum vector will come like this. So my L vector will be over here. Here angular velocity is like this, so curl your fingers this way, thumb goes up like that. So my angular momentum vector is definitely in that particular direction. So it is definitely in this particular direction. Is this clear how to get the direction? Everybody till this point? Perfect. Okay. Let's try some questions. Let's try some questions of angular momentum and then we'll have a short break. So say for example, there is a particle m, it is thrown with some speed under the influence of gravity, and this particular mass goes like this and falls over here. Question is, find angular momentum, number 1 at the start, number 2 at the topmost point, and all of this is with respect to a point on the ground below the topmost point. That means basically you are over here. This is very important. Angular momentum depends which axis you are measuring it from. If you change the axis, if you change the point of reference, the value of the angular momentum only will be different. Okay, so keep all these pointers in mind. Okay, so it depends on the axis, or basically the point about which it is measured, very, very important. It is a vector quantity, that too you can see, it's definitely a vector quantity. Not just that, I'll also put the unit of it. This is kg meter into meter, so kg meter square, and second will be there down, so kg meter square per second. That is the unit of it. Okay, so let's come back to this and solve the question. First point, right over here, this will be my r. Can you see that? This whole thing is my position vector. How much is that r going to be? Okay, this r is going to be whatever is this range, whole thing divided by 2. Range divided by 2. What is the range going to be? It is 2, or rather I can just put, we can put 2u square sine theta cos theta divided by g, and this 2 will also come over here. So 2 cancel. So u square sine theta cos theta whole thing divided by g. So that is basically r. Everybody fine till this point? Okay. Now this velocity u will have 2 components. Actually, one component will be here, one component will be here. So you can see that one component is here, other component is there. So let me just show it. One is here, the other is here. Out of this, which component will it be u cos theta which will matter, or will it be u sin theta which will matter? Remember, whenever you take cross product, whenever the vectors are parallel or anti-parallel, the cross product is 0. So which means out of these two components, only the component which is perpendicular will give you some value. This component is basically useless. This is the component which matters. And yes, that is perpendicular to your r. So that is what will matter to calculate the angular momentum in the first case. Mass is m, r is r, and take the velocities perpendicular component. Because the parallel component will not give only any angular momentum. Is this understood, this concept? Yeah. So just substitute everything. M is m, r is u square sine theta cos theta whole thing divided by g. V perpendicular is u sine theta. So again u sine theta over here. So therefore it will be m is m u cube by g sine square theta, and then we have just cos theta. So that's the angular momentum right over here. Done, dusted. Okay, perfect. Next, let's try to find the angular momentum at the topmost point. When you are at the top, the velocity is u cos theta. Remember, that's the concept of projectile motion. And the position vector will be this. In fact, that r will be the height of the projectile, which is u square sine square theta divided by 2g. Oh, that's the distance, but it is already perpendicular, so don't have to split it. It's already perpendicular, don't split it. Only remember, whenever you have r and the velocity is like this, it will have two components. This component will be useless, this will be useful, because that is perpendicular to your r. Okay, that is perpendicular to your r. Whenever it is parallel or anti-parallel, the cross products are 0. So that component will not matter at all. That's the beauty of cross product. So in the second case, it is again m, r, again v perpendicular. Mass is m, r is h is nothing but u square sine square theta divided by 2g. V perpendicular is u cos theta. So in the second case, it is m, u into u square is u cube, g is there, and we have sine square theta cos theta divided by 2. Oh my god, it's exactly half. It's exactly half. Is this clear? Understoodo? Yes, Capto G is explaining midnight. Yeah, first time after a long time, I think we are doing this midnight session. Earlier in the olden days also we have done this. By the way, we have taken classes even at 4 o'clock in the morning during the board examinations and all those things, if you remember. So yeah, this is probably new for this batch of 20-25 students. Great, great, great. Perfect. Let's go to another question coming up on your screen. A top of 400 grams spins at 10 pi radians per second, actually 100 pi radians per second, and has 10 centimeters as radius of gyration. Question is, find the angular momentum of the top. Find the angular momentum basically of the top. What will you do in such case? Now, the moment you look at this question, you go back a little and you realize, okay, it's no longer a point mass, it's a body, it's rotating. So you have to consider the inertia and the omega value. So definitely for this particular question, the angular momentum will be got by I into omega. But omega is given, I is not given. But don't worry, mass is given, the radius of gyration is given. So moment of inertia is mass of the body into radius of gyration square. Perfect. What's the mass? 400 gram, which means 0.4 kg. Radius of gyration 10 centimeters, which means it is 0.1, and square it. What is omega? It is nothing but 100 pi. Okay, so let's see what happens. 0.4 multiplied by 0.01 multiplied by 100 multiplied by pi. 0.01 and 100 will cancel, so it will become 0.4 pi. 0.4 is 2 by 5. So 2 pi divided by 5. This will be kg meter square per second. So that's the angular momentum of the top. That's the angular momentum of the top. So we have got the answer. 2 pi by 5. That's the answer. Is this clear, my dear warriors? Yeah. Very good. Awesome. Yes. 4 AM class also will be there. The path for the previous question will definitely be parabolic. Yes, definitely. But that has nothing to do with the question. It's just a projectile motion combined with angular momentum concept. That's all. Now, you might be wondering, sir, what if the question is slightly twisted, sir? And you know what? Remember this particular question, which we did just some time back. Imagine the same question is asked, but this time they tell you, hey, listen, the point about which you have to measure the angular momentum is here. So what is the angular momentum of the rod? Okay, so they just ask you this. Question is, they ask you to take this point. Find the angular momentum of the rod about this point. What will you do in such case? First of all, this entire system, you should realize it's a rotation and translation both combined. It's a combined motion. It's a rotation and translational both combined. And just some time back, we saw, since this is the center of mass, the center of mass itself had a speed v, and about the center of mass, this body was rotating with some angular velocity which we just calculated some time back, angular velocity which was 4v by L, if you remember it correctly. So it is rotating about the center of mass with an omega given by 4v divided by L. If you combine these two, you get back rotation and translational combined motion. Is that right, everyone? So what do I do now? I will be like, okay, I have to measure the angular momentum about this point. So how far is this point mass from this particular point? This is going to be your R, position vector, which is definitely L by 2. The best part, it is already perpendicular to the velocity. So the angular momentum of the center of mass will be mass of the body, distance, which is L by 2, into velocity, angle sine 90. Sine 90 is 1. So won't it be MLV divided by 2, guys? Everybody fine till this point? Very good. Next important thing. This is just a rotating body. So for that, it's the angular momentum about or with respect to center of mass. You just use I omega, moment of inertia of a rod, ml square by 12. Omega 4v by L. So what will it be? LL cancelled. 4 goes with 12 3 times, so mLv divided by 3. So this is considering a point mass. This is at that center of mass. If you see the rod rotating, what's the angular momentum? This is exactly similar to what we did over here for finding the kinetic energy of that rod, right? Or in general, any body. It's you consider the center of mass as a translating body, and if you sit on the center of mass, you see rotation, so you find the rotational kinetic energy. So whatever we did in this problem for energy, we are going to do this for angular momentum. That's all. So the total angular momentum of the rod will be nothing but mLv by 2, and then we have mLv by 3, and then the most common mistake comes over here. Till this point everything fine, but the problem is many students end up putting a plus. It's not so simple. Let me tell you that. It could be minus also. You'll be like, sir, what? How can it be minus? See, when we had energies, this energy, that energy, that energy, this energy, if you want to find the total energy, you just add them up. But why did you do that? Because energy was scalar. Direction did not matter. 5 joules plus 7 joules doesn't matter. It is always going to be 12. But 5 Newton plus 7 Newton, that could be 12, it could be 10, it could be 6, it could be so many things, because the directions can be anything. So we should be careful about the direction. Is this absolutely clear? Is this absolutely clear? Okay. So now coming back over here, what is the direction of the angular momentum? R is here, velocity is here. R cross V, R cross V. Thumb is going inside. So the angular momentum in this case is inside. Okay. In this case, omega is like this. Curl your fingers. See where the thumb is going. Wow. Coincidentally, it is again going inside. So both are inside and inside only. Lucky for us, it's going to be an addition. Else it could be a minus also. Got it, my dear warriors? Hence, in this case, 1 by 2 plus 1 by 3. 3 plus 2 is 5. So 5 by 6 mLv. That is the answer. mLv 5 by 6. Do you understood why plus? Because the directions are inside. So hence this direction will also be inside only. This will also be inside the plane of the board. Inside the plane of the board. Is this clear? Okay. So these are all very, very interesting. Great. Awesome. Awesome. Now that we have understood how to find the angular momentum of different bodies in different cases, okay, so let's take a small break and we'll return in some time. So it's a break time. But meanwhile, like the video, and if you have not yet subscribed, subscribe to the channel. Okay, so let's return, guys, in some time. We'll just keep 10 minutes break. This is too much, I feel. Yeah, 10 minutes. Yo guys, I hope I'm audible and visible to all of you. Quickly let me know in the chat box. The time is up. Let's be back from the break. Yes. Ready to continue. Yo, let's go. Welcome back. Yeah, and soon it will be 12 o'clock. Who does not want to attend a 12 o'clock class, right? Come on, guys. Very rarely you get such opportunities. I was thinking that maybe even tomorrow as lecture also, maybe I should take it midnight session. Yeah, 2 days consecutively. It will be amazing, isn't it? Let's see. Okay, so before the break, we have seen angular momentum of a body. Oops. Okay, yeah. So before the break, we have seen what the angular momentum of a point mass is, m r cross v cross product, or you can just use I omega. Either the one of these formulas will give you the answer. If it's a point mass, use this. If it's a big body, moment of inertia is known, you can use this particular formula. Okay, let's do some more questions coming up on your screen. Here we go. If the angular momentum is doubled, the kinetic energy of rotation is what? How many times do you think the kinetic energy of the rotation will change? Chalo, try to figure this bit out. Maybe there is some relationship between angular momentum and kinetic energy of rotation. If you can figure that out, your job is half done. Then it's just simple maths. So let's try to visualize. Kinetic energy of rotation was actually half I omega square. How about this simple manipulation? I will multiply the numerator with I, so it will become I square omega square, and also divide it with I. Why would I do that? Because this I omega is actually angular momentum, so it is squared of it and divided by I. Isn't this? I omega is itself L, so it is half L square by I. So this clearly tells me that the kinetic energy of rotation is directly proportional to the square of length. Angular momentum. Now, what have you done with the angular momentum? You have doubled it. So the square of double, 2 square is 4. That means you have made the RHS 4 times. So the kinetic energy will also be made 4 times. So the kinetic energy of the rotation, is now 4 times the old one. 4 times the old kinetic energy. That is how you get the answer. Is that absolutely clear? How we solve this particular question? Very, very good, guys. Awesomeness. Come on. Let's go ahead. Yes, very good, guys. Very good. Perfecto. Let's move. Next question. If a 0.5 kg mass is moving at 2 I cap minus j cap meters per second at a position of 0, 1, 2, find the angular momentum. Find the angular momentum relative to that particular point. Okay, so let's see how do we do this question. So clearly it is very obvious that in this particular thing there is a reference system and there is a position vector, there is a point mass which has some velocity. So there is no other way to do this problem but to use this formula. Angular momentum is m r cross and v. That's all. So what is the mass? It is 0.5 kg. So it is basically half kg. So now for r and v, I'll do this. Position vector. Well, the position coordinates are given. So vector will be 0 I cap, 1 j cap, which is j cap, plus 2 k cap. That's it. So j cap plus 2 k cap is r. Cross producted with velocity, which is already given as 2i minus j cap. That's all. So what will I get? Half. Now, see guys, there will be so many things which will not materialize. Like for example, j cap cross j cap will be 0. But j cross I will be there, k cross I will be there, k cross j will be there. So there will be 3 terms for sure. So when I multiply j with I, so let's get back over here. You have I, j and k. I cross j is k, j cross k is I. Remember, if you go clockwise, it is positive, and if you go anti-clockwise, it is negative. So use those things and then solve the problem. J into 2i. J into 2i. So I'm going anti-clockwise, so it will be negative. So it will be negative k cap for sure. So 1 into 2 is 2. So minus 2 k cap. Okay, next. 2k into 2i. So 2 2s are 4. K into I. K into I is j. So it is plus j. So plus 4 j cap. Okay. So 2k into 2i. So k into I is plus j. So 2 2s are 4. Next, this minus is there. I'll keep that in mind. 2k into j. 2 into 1 is 2. K into j. K into j is negative I. So it's basically negative I over here. So that is what I get. Alright. So let's see what happens next. Half. Let me put I first. So 2i cap. Then 4j cap minus 2k cap. Is that right? But I have to divide by 2. So it will just be I cap plus 2j cap minus k cap kg meter square per second. That is the answer. Is that absolutely clear? Everyone, how many of you got it? Yeah. Yes. So Govind, which one did you not understand? Yeah. Which one did you not understand? Yeah. If you have a problem in some previous question, you can always rewind back and see it. But otherwise, this was position coordinates x, y, z. So it will become 0 I cap. So that means nothing. 1 j cap and 2 k cap. Okay. Velocity already given. Mass already given. This was the formula for angular momentum. Remember, j into j is always 0. J into I. So j into I negative k. So that's why negative sign. But 2 is multiplied. So 2 times. K into I. K into I is j. And k into j. K into j is negative I. Clockwise is positive. Anti-clockwise is negative. This is the rule for cross product. Is that okay? Everyone got it, Krishna? Excellent. Perfect. So this is how you solve these questions. So I've done quite a few questions on angular momentum, of course, on just finding what the angular momentum is. But obviously there is more to angular momentum when you learn about torque. So first let's go to torque and then let's come back to this and then let's solve more questions, of course. Okay. So we have even related kinetic energy and angular momentum as of now. As of now. Let's now go to the next concept, which is the equivalent of force. So if you go back to this particular table, in translation, we have force F. Here, the equivalent of force is called the moment of force, also called as torque. Also called as torque, tau. Force produces acceleration. Torque produces angular acceleration. So just like force was mass into acceleration, torque will be moment of inertia into angular acceleration. Force was mass into acceleration, torque will be moment of inertia into angular acceleration. Say for example, this thing is there, a body. It's still right now. If I apply a force, it rotates. It started from rest. It got some velocity, so there was angular acceleration. So I have provided a torque on it. But I apply a force like this. Although I'm applying a force, it is not rotating because it has not yet got a torque. And probably the reason for that is the direction in which I'm applying the force is passing through the axis, of rotation. It is not able to produce a twisting force, which is called as a torque. But the same finger at the same point, I just change the direction of it and you see it begins to rotate. But if I apply it like this, it doesn't rotate. So how much force you apply, where you apply, which direction you apply, that matters when you are trying to measure the torque. The same force at the same point might not produce torque, but changing the direction a bit produces a torque. So all these things definitely matter. Yeah. Now, coming back over here. Yeah, there we go. Yes, this thing is there. So torque. Torque is the moment of force, that is the equivalent of force in rotation, and it is a vector quantity. It is like your twisting cause, which produces the effect of change of rotational state, So just like in Newton's laws of motion for translation, Newton's laws of motion for rotation says that the net torque acting on a body, this symbol is for net, the symbol for torque is this, not just this, it is something like this. It's a Greek symbol called as tau, T-A-U, tau. It's like a modified T. Okay, it's not exactly T. Is nothing but moment of inertia into alpha. A very important analogous formula, but for rotation. So as you can see on the left hand side, this is the cause, this is the inertia, and this is angular acceleration. So cause is inertia multiplied by angular acceleration. This angular acceleration is actually called as the effect. How much is it affected by? If the angular acceleration is more, it's affected more. If the angular acceleration is slow, it means it's not affected much. So that's why it's called as the effect. This is inertia of rotation, which is also moment of inertia. So cause is inertia into effect. Very standard result, which we expect. Okay, very, very important. Now, you can also see that the same net torque as per Newton's laws of motion, you can also write this net torque as the rate of change of momentum. By the way, it's a vector quantity. You can also write it as dl by dt, which is nothing but the rate of change of angular momentum. Very, very important. Rate of change of angular momentum. Just like force was a rate of change of linear momentum, torque is rate of change of angular momentum. Meaning, imagine some body is spinning slowly now. Now suddenly it starts spinning fast. It is slowly, then it starts becoming fast. So there is a change of angular momentum. How quickly is that change happening decides how much is your torque. If slowly it is increasing the speed, torque is less. Very quickly it increases the speed, the torque provided is more. And if it is continuously spinning, no change is there, okay, then there is obviously no net torque acting on it. But if I spin this, I can see it slows down. That means the angular momentum, once I leave it, reduces. Why is it reducing? There is a torque. Who is giving that torque? That axis. What is happening at that axis? It's a rubbing. There is friction. So that friction is giving that torque and reducing that angular momentum. So when you turn on the ceiling fan, everybody, the motor inside produces a torque and it increases the angular momentum. There is some angular acceleration. It slowly increases the speed. There comes a time where the fan is rotating at constant speed. Constant speed means angular momentum is constant, so derivative is 0, or alpha is 0 because omega is constant. So when it is rotating at constant omega, it's not like the motor is not giving torque. It's just that the motor gives the same torque as that of the friction and the resistive forces. Both these torques are equal and opposite, and the net resultant torque is 0. That's why you see the fan rotates at constant omega, constant angular momentum. So its rate of change is 0 or alpha is 0. But when you turn off the switch, the motor's torque disappears. The only torque remaining is the torque of friction, which retards it, and that's why it slowly stops. Is this concept of torque clear in your head, my dear warriors? Is this concept of torque absolutely clear in your head? What is torque doing? It's a cause of rotation's change of state. And a torque causes angular momentum to change very quickly and also causes angular acceleration. As simple as that. Understood? Clear? Yes? Yeah. Perfect. So, let's do some questions on this so that you get an idea. If a torque of 10 Newton meter acts on a wheel of moment of inertia 2 kg meter square rotating at 20 pi radians per second. To stop it, how much time will be needed? How much time is needed to stop it? That's the question. Let's try to solve this. Okay. Torque is given, moment of inertia is given, initial speed is given, and I want to stop it. That is also given. Okay. So the torque will produce a retardation. So it is a retarding torque. So it will produce a retarding angular acceleration. Okay. And I know torque is moment of inertia into alpha. Since it is given torque is 10, moment of inertia is 2. So alpha, which is the retardation, will be 5 radians per second square. But this is obviously retarding in nature. It is definitely retarding in nature. Next step, how much time will it take? I think we have to use kinematic equation. If you remember, there was a kinematic equation, final velocity is initial velocity plus alpha into time. Finally, it stops, so 0. Initially, it was rotating at 20 pi radians per second. Alpha will be negative because it is retarding, so technically it is minus 5 and this into t. So 5t is 20 pi. Time, 5 and 20 goes with 4 times, so it will be 4 pi seconds. So it takes 4 pi seconds, not 4 seconds, 4 pi seconds, not 5, 4 pi seconds. Yes. I hope this is absolutely clear. And you don't get any virtual calculators in any exam conducted by NTA. You have to do it by hand in the rough work. There is no other option. Please keep that in mind. Yeah, there is no other option. Very good. Excellent. Moving on. Okay, to the next question coming up on your screen. If a torque of 20 Newton meter acts on a flywheel for 2 seconds, find the change of angular momentum. Find the change of angular momentum of that particular flywheel. That is the question. Let's try to solve this. Torque is given, time for which it acts is given, change in the angular momentum is asked. Usually our torque is just dl by dt. But this torque will obviously be instantaneous torque. If you measure the average torque, instead of d, you should have delta L by delta t. Oh, so this is for average. So if I just want to find a big change in the angular momentum, wouldn't it be just the average torque multiplied by the time? Okay, perfect. So as per this, the change in the angular momentum, well, the torque was constant, so it is 20 only. Time taken was 2, so won't it be just 40 kg meter square per second? That's the change in the angular momentum. Very straightforward. Perfect. The session is going to be till 1 o'clock plus somewhere, I don't know. Now, let me tell you, if you remember linear momentum, impulse, force concept, force into time was change in momentum, which is just impulse. So what will torque into time be called? It will not be called impulse, it will be called angular impulse. So actually speaking, this term over here is basically called as angular impulse. Angular impulse. So angular impulse is just the change in angular momentum, which is just the torque into the time taken. As simple as that. Okay, everybody till this point, absolutely clear? Yes, perfecto, perfecto. Let's go ahead to the next question coming up on your screen. If a torque acts on a sphere of moment of inertia 4 kg meter square, it gains a rotational energy of 100 joules in 2 seconds. Question is, find the torque which acts on it. Find the torque which acts on it. Let's try to solve this particular question. There is a torque which acts on some rotating body and it gains a rotational energy of 100 joules in 2 seconds. Find the torque acting on it. Rotational energy and then moment of inertia. Maybe things are definitely related. Let's try to relate somehow. Kinetic energy of rotation, if you remember, was half I and omega square. This is given to be 100. This is half. Moment of inertia 4. Omega not given. 2 into 100, 200 divided by 4, that is basically omega square. So this goes with this 50 times. So omega will be root 50, which is 25 into 2, which is 5 root 2 radians per second. Is that right? Just check this out. So omega is 5 root 2. So 200 divided by 4 is 50. 50 is 25 into 2. 25's root is 5. 2 remains inside the root. Okay, omega is done. Next step, let's see. I somehow need alpha, only then I can find torque, because torque is I alpha. How do I find alpha? I think omega final is omega initial plus alpha into t. Final velocity is 5 root 2. Initial velocity 0. Alpha do not know. Time 2 seconds. Okay. So basically alpha is 5 root 2 by 2. Therefore alpha is 5 by root 2 radians per second square. Okay, alpha is also done. Last step is torque. Torque is I into alpha. What is moment of inertia? 4. What is alpha? I just got it from here. So 5 by root 2. So basically it will be 20 by root 2 if you want to rationalize it by multiplying by root 2 and root 2. So it will become 20 by 2 root 2, which is basically 10 root 2 Newton meter. So that is the torque acting on it. So torque acting is 10 root 2. Yeah, everyone clear till this point? Okay, so these kind of questions are very commonly asked by NTA guys, if you see, right? Very standard type of questions based on angular momentum, torque, rotational energy and all of that. Okay, so let's do one more question guys, coming up on your screen. If the position vector is given by t I cap minus t square j cap, okay, t square j cap, find for a 2 kg mass, find angular momentum and the torque on it. Find the angular momentum as well as the torque which is acting on it. This was also asked previous year's questions, if you see, very common question guys. So let's try and solve this. Okay. So find the angular momentum as well as the torque. Angular momentum is mr cross v. V is not given. Okay. So let's try to find velocity. Velocity is a derivative of the position. Okay. So take the derivative of this. So derivative of time with respect to t I cap minus derivative of t square with respect to time j cap. So this will just become I cap, dt by dt is 1. This will become minus 2t j cap. Perfect. So let's try to find angular momentum. Angular momentum is mr cross v. Mass 2 kg. R t I cap minus t square j cap. Cross producted with this thing I cap minus 2t j cap. Okay. So what do I get? 2. Then ti into ti, that's 0, because I cap cross I cap is 0. T I cap minus 2t j cap, minus is coming, t into t square, so minus 2t square. I into j is basically k. I into j is basically k. So 2t square k cap, okay, with negative sign. Then minus t square j cap into I cap, first of all this minus sign, t square into 1 is just t square, j cross I is minus k. J cross I is minus k, okay. J cross j is 0, so plus 0, that is what I get over here. So this will be 2, k cap is there, minus k cap is there. So minus 2t square plus t square. So plus 1 minus 2, which will make it minus t square k cap. So this will become minus 2t square k cap. That is the angular momentum. Minus 2t square k cap. Just check this out. Everybody. Yep. Awesome. Next step, let's find the torque acting on it. Torque is derivative of the angular momentum. Okay. So it will be just the derivative of minus 2t square k cap. Okay. So therefore the torque will be derivative of 2t square. T square's derivative is basically 2t and this is k cap. So therefore the torque will be minus 4t k cap. That's it. That is the answer. Because torque was rate of change of angular momentum. And finally we are here. Yes, it's past 12 o'clock. Yes, so finally a midnight session, guys, for the 2025 batch. 24, 23, 22, 21, all these batches we had done already. Okay, all these morning classes, midnight classes, especially during the exam time, it is more. But yeah, it is fun to have it even during the non-exam time. And I feel every day should be like the exam time. You should study like the exam time. Only then the exam time will be chill, or else you will be very tensed, right? Yes, perfect. So that's the answer for the torque. Great. So we have done enough questions on torque, angular momentum, energy, alpha, and all of that. But how do I find the torque? Okay, fine. Torque will be either given to me, or maybe through alpha and I can find it, or through angular momentum I can find the torque. But is there some other way to find the torque? The answer to that is yes. We will come to that as well. We'll come to that as well. But there is a very interesting formula, and I'll show it to you how to find the torque. Let's come to that. In order to find the torque by the force on it, by the force acting on it, it's very simple. You need to know, number one, the axis about which you are trying to find the torque, because if axis changes, the torque will change. From the axis, you will be at some distance, let's say we call it R, at which you will be applying a force. You will be applying a force like this. This force will be making maybe some angle theta with R. This force will have obviously two components. One will be over here, other will be over here. This will be F cos theta. This will be F sin theta. This component is useless. This component is useful, because this force will only pull that body. This force will rotate that body. And that makes sense. Imagine, there is some door like thing. Okay. If I pull it like this, I'm applying the force perpendicular to R. This is my R. I'm applying the force like this. It opens it. It produces a torque. But if I pull out a page like this, it is not producing the torque, because this is R and the force is parallel to it. That is not producing a torque. This produces a torque. Understand that. So that's why this is producing a torque, this is useless. So actually speaking, our torque is nothing but always the distance of point of application of the force, point of application of the force from the axis multiplied by the perpendicular component of the force, multiplied by the perpendicular component of the force. In this case, the perpendicular component is basically F sin theta. The distance from the axis is basically R, and the torque we have already discussed, the symbol for that is tau. So R F sin theta is the magnitude, but if you ask me the vector form, it is position vector of the force cross producted with the force itself, So that gives me the value of the torque. Because of that force. And because of this, you can see the unit of torque. This is Newton, this is meter, so it is Newton meter. That is the answer for this. Is this clear how to measure the torque? It is R cross F. R is here, force is here. You can see sin theta is there. Both are vectors. This is also vector. Naturally, it should be a cross product. R is here, force is here. R cross F. The thumb comes towards you. So that means the torque is, probably, this is a three-dimensional diagram. So maybe R cross F will go like that along the axis in the 3D diagram. So this is how the torque will be. This is how the torque will be. Is that clear, guys? Everybody with me? Absolutely. Yeah. Yes, we can expect similar levels of questions, but maybe plus minus 15 to 20%. Yeah. Yeah. Nothing to be shocked about. I have been taking classes early morning at 4 o'clock during exam times and all those things. So we do that. So just that, out of the blue, I thought ki, okay, students need to learn to stay alive in the night and also sometimes wake up in the morning. One day I will have a morning class and you guys should be attending it. Okay, great. Now let's take some examples and try to figure out if the torque is there or not there. Okay, and which direction it is there. All right. And this is a plate. It is hinged over here. This is the axis, you can say. So it goes in and out of the plane. And I will show you some forces and you will tell me whether torque is there. And if it is there, which direction. So first force is here. Second force is here. Next force is here. Next force, F4 is here. Next force, F5 is here. Next force is over here. Next one is over here. Next one is over here. Next one is like this. This is F9. Then next one is like this. Next one is like this. Enough. So 11 forces. Each force will produce a torque. I want to know which direction will they produce their torque. That's all. Okay, come on, let's start. F1, so basically torque 1 actually. Okay. First force about the axis. Guys, the force is passing through the axis. R will be 0, guys. R will be 0. I think the torque will also be 0. Just think about it. Just think about it. If the force itself passes through the axis, this point will shift here. This will just become 0. So that's why there will be no torque at all. So whenever a force passes through the axis, it will not produce torque. In fact, there are many such forces. Notice even this force. If you extend this, it is passing through the axis. Can you see that? Right over there. Yes. So even F4 will not produce any torque. So even this will be 0. This is absolutely clear. Whenever the force or that extended line passes through the axis, it will not produce any torque. Okay, these are the only two forces which are not producing torque. What about the rest? Okay, F2 is like this, R is like this. This force will rotate this body this way. Just visualize. What will this guy do? It will rotate this like this, right? If you pull it down like this, it will rotate it like that. So definitely it is producing a clockwise torque. So this torque is definitely clockwise. F3, what will it do? About this axis, this is R, it will try to rotate the body this way. Oh, it is anti-clockwise. So torque number 3 is basically anti-clockwise. Okay, what will F4 do? We saw. What will F5 do? If you are pushing it like this, it will try to rotate this thing like that. It is rotating it anti-clockwise. I hope you can see that. So this is R, this is your force. It will rotate it like this. It is anti-clockwise, guys. I hope you can see that. So because of that force, this thing will slowly become like that, right? So it will rotate anti-clockwise because of that force. So torque 5 is anti-clockwise. What will F6 do? If you push it over here, what will happen? If you push it here about this point, just imagine you are pushing it like this. It will obviously rotate like this. It will rotate clockwise like this. So definitely it will produce a clockwise torque. So feel it, guys, how it is trying to rotate it. This force obviously passing like this will push this somewhere here. So it will definitely produce a clockwise torque. Is that making sense to all of you? Yes? Awesome. Yeah. Yeah. Next, torque number 7. This guy will pull this diagram like this. It will rotate it clockwise again. So, you know, it is clockwise. Actually, you know what the trick is? Whichever forces torque you want to see, right? For example, F7, just try to rotate it about that point. You will immediately get it. Just rotate it about the axis about which you are trying to find. So it is clockwise. What about torque 8? Take this, rotate it around that axis. Oh, it is also clockwise. It becomes very easy to find out. F9, best part, F9 is passing through the axis. Can you see that? It is passing through the axis, so it will not produce only any torque. It will be 0. Okay, coming back. What about torque number 10? This torque, rotate it about the axis, it goes like this. So that is also going to be clockwise. F11, rotate it about the axis like this, make it go around, it is going anti-clockwise, right? So this is going to be anti-clockwise. So that's how you figure out the direction of the torque. Isn't it an amazing trick? I hope you guys loved that trick. It's very straightforward, guys. Yeah, perfect, perfect. Let's go to the next question coming up on your screen. In this question, what happens is, there is a plank and it was held by a pandu over here, okay, and another pandu over here. The rod or that plank's mass was m, length was l. Okay. Now what happens? One of them leaves the rod suddenly. Just imagine this. The moment you leave the rod suddenly, what will happen? This guy has run off. This guy has run off. It is like this now. Only the person is holding over here. This guy has run off. What will this rod do? It will try to rotate like this. Obviously, it will try to rotate like this. And in this process, it will end up producing nothing but your angular acceleration, alpha. So the question is, find angular acceleration. Not just that, this person will experience a reaction, normal reaction, on that rod. So find the normal by the person. Find the normal by the person. These are the two questions. Very nice question coming up on your screen. Yes, a torque will be produced. So one pandu ran off. This pandu will experience some some normal force. So what is that normal force going to be? What is that alpha going to be? Okay, let's find out, guys. Let's start with the free body diagram. See, there will be 100% a normal on that rod. mg will act from here like this. Now, if I go by our formula of torque, which I had given you over here, torque produces angular acceleration. Torque produces angular acceleration. If I somehow find the net torque, I think I can find alpha. I know I. So I need to find out torque, but for finding that torque, I need this formula, R cross F. R cross F. Different forces will produce different torques. Okay. So first of all, what will be the torque produced? What will be the torque produced by normal? What will be the torque produced by mg? If I add them up, that is what will give me I into alpha. Net torque produces I alpha. Normal is passing through the point where it is trying to rotate. So the torque produced by normal will be 0, just like in this problem. Whenever the force passes through the axis, the torque produced is 0. Same thing happening here, guys. The torque produced will be big fat 0. So no torque only produced by normal. So 0. Okay, perfect. mg, how much torque will it produce? Okay, no issues. So for that, see how far you are. You are at this distance. This r is basically L by 2. This is basically L by 2. And the angle of the position vector with the force vector is 90. So hence, r is L by 2, force is mg, angle is 90, so sine 90. Remember, torque was Rf sine theta. Torque was Rf sine theta. R cross F, magnitude wise, Rf sine theta. Perfect. Okay. So which means R is L by 2, mg and sine 90. Okay, perfect. So next step, I know what to do. It will be just L, M. Okay, we'll see that later on. First, let's see what will happen on the right hand side. Moment of inertia of the rod about the end. How much is it at the end when the rod rotates? For center, it was ml square by 12. For the end, it was, try to recollect, guys, it was ml square by 3, if you remember correctly. This into alpha. Okay, so some things at least will cancel, like mass, sine 91, L, that's it. So I think I get the value of alpha from this. So the value of alpha that I get, 3 goes on the top, G is there, divided by 2 is also there, L comes below. 3G by 2L, just check this out, 3G by 2 and 2L. Perfect. So alpha is done. Yes. Why did we take R as L by 2? Yeah. We took R as L by 2 because that is the distance at which the force is acting. What was torque? Torque was, go back to the definition, distance of the point where the force applies from the axis. Wherever the force is from the axis of rotation or which you are considering, that is R. So over here also, if you notice very carefully, force is acting at a distance of length by 2. This length was L, so length by 2. mg is the gravitational pull. Where does gravitational pull act? At the center of mass, at the center of the rod. That's why R was L by 2. Okay, alpha is done. But that is not giving us how much is normal. So you'll be like, sir, normal will be mg, n is equal to mg. That's the most common mistake which many students do, but it is not. Rather, if you consider this as our center of mass, the center of mass is actually accelerating. Just think about it. Yes, the center of mass is actually accelerating down. If you're wondering how much is that acceleration, think of this as the center, this as a point on the circle. It is going in a circular path. This becomes just like your tangential acceleration. And tangential acceleration is alpha into r. And r over here is L by 2. So it is actually alpha L by 2 is the center of mass's acceleration. Like, okay, sir, what then? What if center of mass is accelerating? So you know what happens then? If acceleration is down, downward direction is positive. So mg is helping with the acceleration. Normal is opposite to the acceleration. So minus n will be the total mass of that rod multiplied by acceleration of center of mass. Now you might be wondering, where did this come from? Remember, center of mass and its motion chapter. I have given this to you. Net force is total mass into center of mass's acceleration. If each particle has different acceleration, when you find the net force, the acceleration that you get is not any random particle's acceleration. Rather, it is center of mass's acceleration. So that's why m into ACUM. That is the tricky thing. And that's what I told you. Center of mass is a silent killer chapter. From nowhere it will come off. You never know. So guys, we just have to find the normal. Center of mass acceleration is alpha L by 2. Alpha itself, we just got it from here. Just check this out. Alpha itself was 3G divided by 2L. And this is L by 2. So LL cancels, 2 cancels. So 3G divided by 4. That is ACUM. So just put 3g divided by 4. This mass is as it is equal to mg minus n. So therefore n will be, take it on the other side, mg minus 3 mg by 4. 1 minus 1 by 4, 3 by 4 is 1 by 4. So it will be mg divided by 4. So the normal acting on the rod by this Pandu is mg by 4. We have found out that answer also. Isn't it a beautiful question? Silent killer question. Silent killer chapter, sorry. Yeah. So it's a very, very nice question. Let's go to another question, guys. Let's go to another question coming up on your screen. This is another brilliant question. Let's see if you guys can figure it out. Very few people solve this, but I really hope you guys solve this. Okay, so as you can see, there is a hollow sphere and a solid sphere. Both of them, just imagine like this globe is a hollow sphere. Imagine if it is full, then it is a solid sphere. Both of them are at rest. Body number 1, body number 2. Radius is same, masses can be anything, it's not given. Okay, so be very careful. Mass may be in fact different. It is not given to you only. Is that clear? Yeah, mass not given to you. Now imagine a force is acting on it for some time. Both of them begin to rotate. First it was at rest, the force begins to act tangentially, it will rotate, it will gain some angular momentum. Question is, after some time, compare the angular momentum of 1 and angular momentum of 2. Less than, equal to, more than, can't say. What do you think the correct answer should be? Chalo, figure this out. Okay, just figure this out. I want everybody to give the answer. Oh my God, Ratan Tata passed away. Is that? That is very sad news. That is really heartbreaking. I mean, Ratan, if that is true, I'm not really sure if that is the case. I'll have to verify the news though. But since Krishna is saying this, I'm pretty sure it will be correct. Oh yes, it is true. It is true. It is heartbreaking, guys. And Ratan Tata, you know, the famous entrepreneur and very, very noble character who was a very big philanthropist who donated a lot of money for the poor, the needy, and even when, you know, things are not going bad, and is also, you know, leading so many groups, be it Tata Motors, Tata Salt, even Tanishq, and then Starbucks, and then what do you say, even Big Basket, and Tata Steel, and the Taj Hotels, and so many industries are there. And you know, the man behind this particular group of industries is none other than Ratan Tata. So, which was, and Tata Group is actually a very old group, more than 100 years back, you know. In fact, the entire city of Jamshedpur was built on one man's principle, Jamshedji Tata. And this is very, very heartbreaking. Such kind of people are very rare to find and very, very progressive, and just imagine, they could have definitely gone out of the country and maybe made some wealth out there, but they decided, no, let's not just make money for us, but also provide employment to not 1, 2, 3, 4 people or tens people, hundreds people, but lakhs of people. So they have really provided employment for so many of them, and that is something which we all should be proud of, and a national icon. That's what I would say, a national icon, right? So they are people who we should look up to, not just some random Instagram or some random social media influencer. Some people are really good, like for example, Food Farmer, such a nice Instagrammer or YouTuber who gives a lot of health-based information, right? So many people are there who do good work, but not those people who do it some chapri, some very nonsensical things which they do. Rest in peace, such a great soul. All right, so let's compare this, guys. What will happen after some time? See, if you notice carefully, R is same, angle is same, force is also same. So can I say the torque, which is Rf sine 90, is basically the same for both? Time is also the same for both. And we have seen just some time back, torque is change of angular momentum by the time taken. So this torque and time is same. Therefore, can I say delta L is also going to be the same? Delta L is also going to be the same. Okay. Delta L means final minus initial angular momentum is going to be the same. But wait a minute. They were at rest. So initial will be 0. Final minus 0 is going to be the same. But anything minus 0, is that anything? So the final angular momentum is just going to be the same. So hence the correct answer over here is a big fat equal to. Not more than, less than. It is just equal to. This solid, hollow doesn't matter. Moment of inertia didn't matter in this question. So that's why it is a very tricky question. Is that clear? Very nice. Very nice question it is. Great. Let's move to the next question coming up on your screen. This is also a brilliant question. Let me tell you that. So here what happens is, you have a small ball, and this ball is thrown horizontally with some speed u, mass is m. This ball will go like this and it will fall. From the point of projection, if you measure the torque, if you measure the angular momentum from the point of projection, if you measure the angular momentum, what can you comment? The angular momentum will dash, and in that dash you have to fill up whether it will increase, whether it will decrease, whether it will remain constant or something else at only. What do you think will happen to the angular momentum? That is the question. Beautiful question. Now, what generally people do, I have seen that you go take a general point, the velocity will be completely different, the r will be different. If you stand here, r is different, velocity is different, angle will keep on changing. So it's not so easy if you go by mrv sine theta. Why is it not easy? Why is it not easy? Yes, because v will change, distance will change, angle will change. So not so great way of doing this problem. No issues. Maybe torque will help us because torque and angular momentum are also related. So we'll be like, sir, how? Okay, no issues. See guys, at any point wherever you are, mg will be like this, your position vector will be like this. Actually, this will be your r, this will be your mg. Like, sir, even here r is changing and even the angle is changing. But I'll tell you what, when you measure this torque, if this is our force, this is our r. Usually we write torque as r cross F. That gives me the torque. But you can also write torque as, R is there, but what you do is you take the perpendicular component of the force, this one, perpendicular component of the force, F perpendicular, which is nothing but F sine theta. But there is one more way. You leave F as it is. Instead, what you do is extend that line of force, and what you do is drop a perpendicular. This is R perpendicular, and you will see that since this is theta, why is that theta? That is because this is theta. So this is actually speaking R sine of theta. So R F sine theta or R sine theta into F, one and the same thing. So you can just write it as R perpendicular into F, where R perpendicular is R sine theta. One and the same thing magnitude wise. All the three ways are equivalent, gives you the same answer. Sometimes you will find this is easy, like for example, force is perpendicular and you can do it. Sometimes you can find R perpendicular and it makes your job easy. So for example, in this thing, we didn't have to split anything because the force was already perpendicular. But here, you know what? R is at an angle. I have a feeling, how about extending this line of force, and you will notice very easily that this is basically your R perpendicular. This is basically your R perpendicular. Can you see that, guys? What is R perpendicular? Everybody with me? Yeah. So as this mass comes down, as our torque which is there of mg, which is R perpendicular into that force which is mg, this will increase. This will increase. If the torque increases, what else will increase? Obviously, rate of change of angular momentum will obviously increase. Now you'll be like, okay, so what? Initially, angular momentum was 0. Then the slope of angular momentum is increasing. Think graphically, guys. It becomes very easy to understand. If this is time axis and if this is angular momentum axis, initially angular momentum was 0. This is what it is. dl by dt means slope. Slope is increasing. So slope is increasing, which means there is only one way this can go. So here the slope is like this, then the slope is like this, then the slope is like this. So the slope is increasing. That means angular momentum is definitely increasing. Hence the answer to that is it will increase. So we get the answer via torque and slightly unconventional method. Very, very unconventional method. Is this absolutely clear? Understood how we did this? It's a beautiful concept relating torque and angular momentum. Great. Now, there are also pulley questions which you can solve using this. Let's do some pulley questions as well. So say for example, you have a pulley like this. There is a mass over here. There is 3m mass over here. This pulley is held at the top. This is having a mass of 2m. Think of this like a disc of radius r. The question is, can you find the acceleration? Can you find the acceleration of the blocks? What is different in this question is that first time you are seeing a pulley with mass problem. Pulley with basically mass problem. So what do you do when basically pulleys have masses? Don't worry, it is not that scary at all. It's very simple, just one small change, you have to draw the free body diagram for the pulley also. And the difference is, the pulley is not moving up and down, it's just rotating. So rotating equations will come, that's all. Apart from that, everything is straightforward. Okay, so let's start by drawing the free body diagrams. So what are the free body diagrams of this mass? It will have mg over here, some tension over here, some weight over here, tension over here. So tension mg, tension 3 mg. Obviously this guy will accelerate down, so A. This guy will accelerate up, so A up. But at the same time, for the pulley, tension over here, tension over here, this wall, this roof will provide some kind of normal, and there will be angular acceleration which is alpha. Angular acceleration which is alpha, and apart from that, the disk's own weight which will be 2 mg, which will be 2 mg. Now, if you write the equation for this and this mass, say for example 3m mass, weight is down, tension is up, acceleration is down. So wherever acceleration goes, that's where the positiveness is. So I will just say 3 times of mg down minus the tension is equal to 3m into A. For this mass, tension and acceleration upwards, so tension minus mg is opposing the acceleration, is mass into A. For this, don't write normal is tension plus 2 mg, that is of no use because it is not going up and down, it is rotating. So what matters is the torque over there. So the torque by normal plus the torque by 2 mg plus the torque by tension plus the torque by the other tension, this is moment of inertia of the disk into alpha. That is how the equation will be. Net torque is I alpha. Net torque is I alpha. Torque by normal, because normal is passing through the axis, therefore 0. Torque by the weight, again passing through the axis, it is 0. Torque by this tension, can you see? It is clockwise. Torque by this tension, it is anti-clockwise. So one is clockwise, see this, R cross F like this, R cross F anti-clockwise. So definitely they both will end up cancelling. So because of this, alpha will come out to be 0. But if alpha is 0, it is not angularly accelerating, then how will A come? Because I know one thing for sure. If you look at that disk, right? All the points on the disk have this tangential acceleration. So that same acceleration continues here also and here also. So this A tangential is basically the same, which is alpha into R. So basically A is alpha R. So A is technically alpha R. So if alpha is 0, A is also 0. But that can't happen. So something we have done wrong. And deliberately I did this for you. I made this mistake so that you realize this. The mistake that we have done is that the tensions on both sides can't be equal. In fact, if this is T1, this is T2. Yes. So this is T1, this is T2. So whenever pulleys with mass comes, you will see the tensions are not necessarily equal on both sides. So that is the main catch for these pulley problems. Yes, different tensions. Keep that in mind. Only then alpha can come. So over here, guys, this will be T1, this will be T2. So same thing over here, tension 1, tension 2. Now if you notice tension 1, R is R, force is tension, angle is 90 degree. So therefore it will be R into T1 into sine 90, which is 1. Plus, for tension 2, this is R, but it is anti-clockwise, so better to put minus sign, R into T2. Moment of inertia of the disk, mr square by 2. Alpha is A by R. Alpha is basically A by R. That is what you will get. So a lot of things will cancel, like this R and this R, this R, this R and this R. And finally, we will get T1 minus T2 is equal to MA by 2. Now, look at all these equations, T1 minus T1, T2 minus T2. If you add them, no, it will become very, very easy. So basically, just add all the three. Add all three equations. Add all the three equations. So what you will get? See from here, 3 mg I will get. Minus T1 plus T1 cancel. T2 minus T2 cancel. Minus mg also I will get is equal to here 3 ma, here ma, and lastly over here plus ma divided by 2. Perfect. 3 mg minus mg is nothing but 2 mg is equal to 3 plus 1 4, 4 plus half 4.5, which is 9 by 2. 9 by 2 basically ma. mm cancels. So therefore a will be 2 2s are 4, g is there, divided by 9. So 4g by 9 is the acceleration. Done and dusted. That's how you solve these questions, where pulleys have mass. Catch is that the tensions will not necessarily be the same, it will be different. So you need to be little bit careful in the free body diagram, or else you can't solve the question. Yeah, awesomeness, awesomeness, perfecto. Now there are some questions where you will see there is no alpha only. In fact, those are also very nice questions where equilibrium is achieved. So questions where you have some kind of equilibrium. When I say equilibrium, what does it mean? It means it is basically at rest, and there are two conditions for this. First is net force is 0. That means translation is absent, and next is net torque is 0 about any point. That means rotation is absent. This equilibrium where bodies are at rest, you will see net force is 0, net torque is 0. You can also use this concept for toppling questions. Toppling, on the verge of toppling. Something is there, it's about to topple, it's about to fall. Just before it is falling, torques are balanced. Something more happens, it will roll over, it will topple over. So those kind of questions or equilibrium questions, both of them have the same concept. So when it is on the verge of toppling, you use this. Is this clear? Yeah. Yeah, you can expect the flashcards delivery within usually 1 to 3 weeks, anywhere between that. Usually it is 1 to 2 weeks, very rare cases 3 weeks maximum. So let's do some questions on this so that we get an idea. So let's say, for example, we have this rod and it is held by 2 strings here and here, and this is the roof. This rod has a mass of m, length of L, and there is some another mass 2m which is kept at a distance of L by 4. L by 4. I call this string number 1. I will call this string number 2. The question is, find the tensions in both the string. Find the tensions in basically both the strings. Let's try to solve this. Okay. Because there is a mass, point mass, which is attached on the rod, that too closer to the left hand side. So it doesn't make sense the strings will have the same tension. In fact, it will have different tension. Obviously, it is not symmetric. If it was exactly in the middle, it would be equally balanced, but it is not. So obviously one side will have more, one side will have less. So if you draw the free body diagram of the rod, I can say tension 1 on this side and the other string will pull it up by some new tension T2 on the other side. Yeah, perfect. Yes, perfect. Now, apart from this, this 2m will also have its own weight, which will be nothing but 2 mg. Which will be nothing but 2 mg. Everybody gets this point? Perfect. The rod also has its center of mass here and its own weight will be nothing but mg like this. Oh, so that is the catch. Many people do not show the forces at the right places. If you show it at the right places, only then answers will be correct. So center of mass of the entire rod is exactly here. So that's why mg over there. And that distance of mg obviously will be L by 2. It will be L by 2. That's it. My job is done. Now, no other forces are there. Net torque is 0. Net force is 0 because this is now a question of equilibrium. This is now a question of equilibrium. Perfect. If it is now a question of equilibrium, net force is 0. So, okay, net force is 0. So, tension 1 plus tension 2 will be mg plus 2 mg. 1 plus 2 is 3, so 3 mg. But that's the problem now. I don't know T1 nor T2. How do I find it out? So then we go to the next step. What is the next step? The next step is, if it is in equilibrium, obviously the net torque is 0. But about which point? Any point. You can choose this, anywhere you can choose, that torque will be 0. But obviously we are not stupid to choose some weird point. We'll choose a point which will make our calculations easy. So how do I make my calculations easy? When the torque calculations are easy. And torque becomes 0 when the force passes through the point. Remember that. R is 0. So try to make as many torques 0 as possible. If you can make even 1 or 2, that's a good enough strategy. So how about making the calculations about this point? The left end. The left end. Because it is most likely going to make it easy. You can also choose the right end, nothing like that. Because T1 is passing through this point or T2 is passing through this point. Will make my job easy. Why will the center of mass be at L by 2? Because it's a uniform rod. For uniform rods, remember, uniform geometries, center of mass is at the geometrical center. Unless it's some non-uniform rod. Make sense? Yeah? Yes. Very good. Awesome. So now what? What next? What next? Yeah, once this is done. Once this is done. Yes, measure the torques. Torque by T1 plus torque by T2 plus torque by mg plus torque by 2 mg, the whole thing should be 0. What is the torque by T1? It is 0 because it is passing through the point. What about torque 2? This is giving anti-clockwise torque. Distance is L. Force is already perpendicular. So it will just be L into T2. Why minus? I'm taking anti-clockwise torque as negative. mg's torque is like this clockwise, so I will take it positive. 2 mg's torque is also clockwise, so I will also take it positive. This is 0, this is negative, positive, positive. Do you understand? Signs play a very important role. If you just write magnitudes, gone, negative marks. So plus mg is at a distance of L by 2, R is L by 2, force is mg. 2mg is at a distance of L by 4 into 2mg. This whole thing is 0. Okay, so take it on the other side. 1 by 4, this is, sorry, 1 by 2, this is also 1 by 2. So L by 2 plus L by 2 is complete L. So Lmg is equal to L into T2. So therefore, T2 is basically mg. Oh, T2 is mg, guys. So just put mg over here. That's it. I think we will get T1. T1 plus mg is 3 mg. Therefore, T1 will be 3 minus 1, which is 2 mg. So we found both the answers. This one and this one. That's it. Is this absolutely clear how to solve these questions on equilibrium? Yeah? Perfect. Yes. Awesome. Now, let's do another question. So we did a question on equilibrium. We'll do more questions. Don't worry. Let's do a question on toppling now. Let's do a question on toppling. Question is, find the force needed. Find the force needed to topple whatever I am showing you now. Find the force which is needed to topple this particular body. There is this box. It's lying on a ground, okay, and assume that friction is enough to prevent friction is enough to prevent the slip, to prevent any kind of slipping. That is also mentioned, and the height is h, the breadth is b, and the force which you are applying is right over here. So find how much force needs to be applied so that it just begins to topple. That is the question. Now try to visualize there is a box, somebody is pushing it from the top. What will happen? It will try to topple. But about which edge or point or axis will it topple? Will it be this, 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 this? Where will it try to topple, guys? Imagine somebody is pushing that box from the top. It will leave the contact over here and it will topple like this, I think about this point. Is that visualized, everyone? It will try to topple about that point. I hope this is absolutely clear. Yeah? Pravina, hold on, bacha. Okay, great. After this question, we'll have a small break. Don't worry. It will have a toppling effect about this particular point. Perfect. So now let's try to measure everything about this point. So I need to first of all show the forces. One of the forces already shown. Mg will act from here, guys. Mg will act like this. Friction will act from the ground surface like this. Normal, none of these points will be in contact. It will completely shift over here. So this is where normal will be. Reason is this box now would probably be slightly like this when it is just on the verge of toppling. So, everything has shifted here and it is about to topple. That's the reason for it. Because you are pushing the box from here. This is how you are pushing it. That's the reason for it. So none of these points are in contact. Only point of contact is here. So normal will act from the edge where it is toppling. Okay, perfect. Now, what will I say? I will say net torque is 0. Net torque is 0 about the bottom right side point. Okay, fair enough. So torque by that force, torque by friction, torque by normal, torque by mg together is 0. Best part for this point, friction and normal both are passing through that point. So no torque because of normal and no torque because of friction. 0 and 0. This force about that point will try to rotate it clockwise. So it will be positive. This mg will rotate it anti-clockwise about this point. So negative torque anti-clockwise. So therefore, plus force is at a distance of h. Force is at a distance of h. So plus h into F. This is 0, this is 0, this is negative. mg, this is center of mass. So guys, this is exactly breadth by 2. So it will be b by 2 is r and force is mg. This is 0. Do you understand why this is b by 2? Do you understand why this is b by 2? Yeah, perfect. So then what will happen? hf is equal to bmg divided by 2. Therefore, f should be bmg by 2h. If the force is this much, then it will be beginning to topple. It will start to topple. Anything more than this, it will start rotating like that. Is this absolutely clear how to solve this question? Perfect. Awesome. Awesome. Great. We'll take a short break and we'll return. Yo, finally we are back. Welcome aboard. Just before the break, we are doing questions on equilibrium and toppling. Yep. Ready, guys, to knock it out? Yeah, just couple of more minutes. We are going to do angular momentum conservation and a few more problems on equilibrium and all that. And most of the chapter is almost like done. Remember, rolling basics are you need to know, but apart from that, slipping and all that is not there. So very basic rolling motion is what you will be needing, but apart from that, you will not need much. Okay, so let's continue our discussion. Let's go ahead. To this particular question. Imagine there is a block over here. It is kept on a inclined plane like this. The question is, if this is theta, this is h, this is b, the question is, find theta after which the block topples. Assume no slip. Assume there is no slipping because of enough amount of friction. Very interesting question. See, imagine you are standing normally, then both your legs get the same pressure, same force, same normal. But when you are standing on an inclined plane, one of the leg, tries to lose contact, other leg is pressed more. Just you try to stand on a ramp or a slope, you will feel that pain. One leg is pressed more, one leg is pressed less. So same thing over here, you will see that in this situation, these sides will have more normal as compared to this side over here. And as you increase the angle more and more, there comes a point where that entire object will topple over. So now when it is on the verge of toppling, the angle is increased to a decent amount. The angle is increased to a decent amount. How will that diagram basically look like? I think it will be something like this, where when it is on the verge of toppling, all these points have lost contact, because when it is on the verge of toppling, obviously it will topple over this point. Understand that. So all these points have almost lost contact, and the entire normal force has shifted here and it starts to act here. So the normal force has shifted here. That is the first thing that you should notice. Is this making things very obvious? Yeah, because all these points would have lost contact and the normal force would have shifted here. Apart from that, the friction still would act over here only. Apart from that, the friction will still act over here along this line. Now, if you see about this point, normal is passing through it, friction is passing through it, so it can't give any torque. Exactly. So the only force remaining is mg. Now think about it. If mg acts from this side, right hand side of this point, it will produce a clockwise torque, which means it will try to bring it back. Clockwise means like this. So it will push it back onto the floor. But if mg acts from this side, it will produce an anti-clockwise torque, which means it will topple. So when it is just about to topple, where will mg be? mg will pass exactly through that point. When it is on the verge of toppling. This is on the verge of toppling. And whatever questions we have, it is always on the verge. That's what I also mentioned over here. Toppling means not it is already toppling, it is on the verge of toppling. So always net force is 0, net torque is 0. So here also you will see all the forces are concurrent. All the forces are concurrent. That's why net torque is 0. Since all forces R is equal to 0. All the forces, position vector of those forces is 0. It is passing through the axis. So no torque at all. Is this absolutely clear? Everybody with me? Is this absolutely clear? Let me know quickly in the chat box. Yeah, perfect. So then you will be like, sir, nothing is there, no torque is there, then what is there to calculate? In fact, this diagram is good enough to make all the calculations. I'll tell you how. Just extend this line, right like this. Okay. Draw a horizontal line right over here. We already know that this particular angle is theta. Why? Because this is theta. If this is theta, this is 90 minus theta, correct? And then this is theta, and then this is theta, and so on and so forth, correct? All alternate angles. The moment I extended this line, I can see a nice little triangle over here where this side is basically H, this side is basically B, this is 90 degree. So in that right angled triangle, can you see that tan of theta is basically B by H? So basically the question was that find the angle for which the block topples. So theta is nothing but tan inverse of B by H. That's it. That is the answer. After this angle, it will topple. Before this angle, it will not topple. At this angle, it is just about to topple. A small disturbance can just topple it over. Is this absolutely clear? Such a brilliant question. Everybody? Yeah. I hope this is clear. Cool. So let's proceed ahead. Let's proceed ahead to one more concept. And actually the questions on this are also very rare, but if it comes, you should know. See, again, let me go back over here a little bit when we discussed translational and rotation. See, we said kinetic energy is half mv square, rotational energy is half I omega square. So force was ma, torque was I alpha. Is there something for work also? Work is force into displacement. Force into displacement. In rotation, it should be equivalent of force, which is torque, into angular displacement. Exactly. So you will see that in case some question comes, very rarely it will come, but still if it comes, work done by a torque, work by a torque, if it comes, then that work is just nothing but the torque multiplied by the angular displacement. Don't get scared about the units, it is still the same, it is still in joules, it's not very different. This is okay if basically the torque is a constant. Torque is a constant. But if torque is not a constant, then you have no other option but to multiply torque with d theta, and then you have to basically integrate it, that means add it up to get the total work. When do you do this? When basically torque is variable. When the torque is basically variable. And whenever integration comes from some initial point to final point, it also means you have to find the area under what versus what? Torque versus displacement. Torque versus angular displacement. Angular displacement. That will give you the torque acting on it. Work done by the torque. As simple as that. So this is for constant torque, whereas when the torque is not constant, then you have no other option but area under the torque versus angular displacement graph. So this is the work done by a torque in moving an object. Very, very straightforward questions come on this. I mean, nothing very great. But before moving ahead, let me also remind you that you can also write power. So the power of the torque that power is simply put the torque into, instead of velocity, you will have angular velocity, tau into omega. So this is the formula. Torque into omega will give you power of that particular torque. Let's do some questions. Let's understand it. If a torque of 40 Newton per meter acts on a wheel, okay, of moment of inertia of 2 kg meter square for 10 revolutions starting from rest. Find final angular velocity. Question is, find the final angular velocity. Let's try to read the question again, see what is happening, see what can be used. There is a torque acting on a wheel, moment of inertia is given, it completes 10 revolutions, and then you have to find what is the final omega. Immediate reaction might be, sir, can't we use, kinematic equations? Yes, you can. But I feel there is a much simpler approach. We can avoid kinematic equations also. Like, sir, how do we do that? See, this torque acts for 10 revolutions. So definitely there is some work done by the torque. And what does work do? Try to remember work, power, energy chapter. Any work that you do changes the kinetic energy of the system. So definitely there will be a change of the kinetic energy of rotation of that particular wheel. Oh, perfect. So the work done, we know, is torque into the angular displacement. The change in the kinetic energy is final minus initial. So half I omega final square minus, initially it was at rest, so minus 0. So I have just used work kinetic energy theorem. I think it will give me the answer very easily. I don't have to find the area because torque is a constant, and whenever it is a constant, it becomes very easy. I can just multiply by 2, multiply the 2, and I will get the answer. Okay, so what's the torque? It is 40. What is the angular displacement? Remember, it is revolutions, and each revolution is 2 pi radians. So don't forget to multiply by 2 pi is equal to half moment of inertia. It is basically 2. Omega final, I do not know. Perfect. 2 has cancelled. 4 into 2 is 8. So 8 is there. 0 will make it 800, and this is pi. And on this side, I just have omega final square. So what will omega final be equal to? So 800, well, I can just write it 400 into 2. 400 is a perfect square, which is 20 root 2, and this pi will also remain inside. So 20 root of 2 pi radians per second is the correct answer. Very easily I get it using the concept of work and kinetic energy. Is that clear, everyone? Let's do one more question. Coming up on your screen. Get ready for it. If it is told to me, the power of a motor is constant and the axle begins from rest, the angular velocity is proportional to some power of time. The question is, what power of time is it proportional to? What power of time is that angular velocity proportional to? That is the question. Okay, so let's try to do this. Yeah. Now, power is constant, and power by Formula we know, it is torque into angular velocity. Power is constant. Omega, we have to find how is it proportional to time. Somehow I need to do something with the torque. Other than that, there is no other way. Torque is I into alpha. Well, okay, I into alpha. But then what else can I do? Oh, wait a minute. Alpha and omega are related to each other. So I into alpha is rate of change of angular velocity. Oh, perfect. So bring dt over here, bring I over here. So P by I, and then there is dt is equal to omega d omega. Let's bring this here, let's bring that here. So omega into d omega is equal to P by I into dt, but at the same time, let's also integrate. Starting from rest means 0. So at some time t, there is some omega. Omega raised to 1. Omega raised to 1's integration is omega raised to 2 by 2, and this is 0 square by 2, putting the limits. P by I is as it is, and here I have t minus 0. So therefore I get omega square, this is 0 only, is equal to 2 times P by I into t. Therefore omega is root of 2p by I into root of t. So omega is directly proportional to t raised to half. Hence the answer is half. The answer is half. Is this absolutely clear, my dear students? So this is how we found out how omega is related to time. So these are again standard questions which you can get where they involve the concept of work, torque, or power produced by a torque. Very straightforward questions. Not at all difficult. Okay. What about the concept of rolling? Do they ask questions on rolling? Well, usually they don't. Now the meaning of rolling is that, because this is a deleted part of the syllabus, but still I will tell you some basic things about it. The main thing about rolling is that this point of contact which is there, as this body moves ahead, this body will move like this. It will also have some angular velocity. As this body rolls like this, okay, this body rolls, every time this body makes a contact over here, that velocity of that point of contact is always going to be a big fat 0 at every instant. At every instant. Very, very important. So this is one thing which you should know for rolling. Second thing which you should know is this velocity is related to this omega. Yes, this will have definitely some radius. Let's say I call it r. So this velocity will be equal to omega into the radius of that wheel, always. Another important story which you should know for rolling. Okay. Next important thing. The friction which acts here can either act here or can act here, depends on the situation. But whatever friction it is, it will always be static in nature. Why? The point of contact is at rest. It's having no velocity. So there is no rubbing, there is no slipping. It's a rolling motion. The point comes in contact, makes that contact, and then it leaves. Then the new point of contact comes. It never slips or skids. Slipping and skidding example is you press the accelerator hard, there is a burnout, or you are drifting a car, or you are applying the brakes suddenly. Rolling is what happens on a regular basis. You are normally driving, there is no skid. You don't get that noises. So when that noises and that sound and that smell, sparks come, that's when slipping, skidding is happening. So that's why the friction is static in nature. It can act either ways. Can act in either direction, depending on the situation. And because the friction is static, because the point of contact does not move, all these things you will see the work done by it is 0. So the work done by friction, is always going to be 0. This friction which can act in either direction often is also called as the rolling friction. So a lot of times students think rolling friction is a new kind of friction. No, it's actually static friction. It's actually static friction, nothing different. So all the properties, Fs is less than Fs max and Fs max is mu Sn, all those things are still valid. So there is no denying those things. It's just that the work done by it is zero. It will never ever consume energy, nor will it give energy, because no displacement. So why work? Work is force into displacement. It's at rest. Okay, so these are the main things that you should know about rolling. Let's say, for example, we get a question like this. Let's say we get a question like this. There is a solid sphere, and maybe it was somewhere here and it came over here. This is a rough surface, and after some time, because it reached here, it will definitely have some velocity. The question is, can you find this velocity given the fact that this particular thing is h. It is also given this is a solid sphere. This is also given to you. Can you find the velocity when it comes over here? It started from rest. All these things are given to you. Okay, it starts from rest. It's a rough surface. It rolls down, and by the time it comes down, it has some velocity. So normal thinking, yes, it was at some height, it has some potential energy, it got converted into kinetic energy. So immediately students start saying it's the gravitational potential energy which got converted into kinetic energy of that ball. But that is slightly wrong. I'll tell you why. Because it not only has this velocity, but it also has, do not forget, angular velocity. So strictly speaking, it is not just kinetic energy of translation, but it also has kinetic energy of rotation. Number one. Number two, it's rough. How can you even conserve energy? That is the problem. See, energy is conserved when friction-like forces are not doing work. Oh, wait a minute. What did I just say? Friction, normal, tension, evil forces, non-conservative forces. They should not be doing anything. Even if they are there, they should be silent. That means not doing work. Oh, so we know that static friction in rolling doesn't work. It doesn't work. This immediately means if it is not working, therefore mechanical energy must be conserved. Mechanical energy is definitely conserved. So this is a very important takeaway for rolling motion, guys. So for rolling motion problems, you can definitely conserve energy because friction is not going to do work. So be happy about it, and that's why this statement is perfectly correct. There is nothing wrong. So what is the gravitational potential energy? It is mgh. What is kinetic energy? Half mv square. What is rotational energy? Half I omega square. What is moment of inertia? It is 2 by 5 mr square. What is omega? We just know that v is nothing but omega r. How do I know this? Because for rolling motion, that is the formula. V is omega r. V is omega r. Okay. So coming back over here, omega will be nothing but v by r whole square. So let's see what all happens over here. This r square and this r square will cancel. So I am just left with mgh is equal to mv square by 2 plus 2 cancels 1 by 5 mv square. So cancels, so gh 5 2s are 10, so 5v square plus 2v square, which makes it 7v square by 10, or 10gh is equal to 7v square. V square will be 10 by 7gh, so v will be root of 10 times gh divided by 7. That is the answer. We got it. So that's how you can solve these questions of rolling from some particular height. Because rolling motion, there is no reason why energy should not be conserved. It's definitely going to be conserved. Then I have also seen one question like this. which will say you have a wheel like this. Can you find the velocity of this point, this point, this point, you know, and this point, so we already know. Can you find the velocities of these 3 points? The answer is definitely yes. So find velocities of the points which have been marked. How to do these kind of questions? How to do these kind of questions? See guys, I told you over here only. Where is it? Here. This point is at a rest. This point is having v velocity and the angular velocity is omega. So for such problems, what you can do, one simple trick is there. Since this point, the contact point, is basically at rest. If you remember our discussion of any body, our discussion of any random body, and remember this was the axis, and all the points, maybe over here, this had some velocity, maybe over here, this had some velocity. If you are here, the velocity is less. If you come closer, velocity is even less. It's slightly more here. As you go closer and closer to the axis, the velocity becomes less and less. So the axis is that point which is basically going to be at rest. So can you not see, this is actually like the axis which is at rest. So the contact is at rest. This also means this is like the axis of rotation. This is definitely the axis of rotation. Is that making sense, guys? If you have any body, all the points which are far away have more velocity, closer to the axis less velocity, on the axis zero velocity. So this body which was translating, rotating, it's as if it's rotating or toppling about this particular point, rotating about this particular point. Oh, this makes my job easy now. I'll tell you how. If it is rotating with some angular velocity like this, to find the velocity of any point, all you need to do is join that point with that axis, and the velocity is definitely going to be perpendicular to it. Just see how much that distance is. Well, this distance is definitely 2r. So this velocity will be omega into r. R over here is 2r. R over here is 2r. So the velocity of point 1 is omega into 2r, which is omega r into 2. Usually omega r is the velocity of the center. So it is basically 2v. If you are asking, sir, what is this v exactly? This v is basically the velocity of the center. Is the velocity of the center. And remember that v will be omega r. Oh, so the topmost point has double the velocity as this point. Then what about this point over here? What about this point over here? No issues. Join a line from the axis to this point, the velocity will be in this direction. So if you want to find this velocity, let's say number 2, I need to know this distance. No issues. This, remember, this is r, this is also r, this is perpendicular if you draw a triangle like this. So this is root 2 times of r. This is nothing but r root 2. R root 2, that is what this will be by Pythagoras theorem. And this is our velocity. Oh, perfect. So that velocity will be again omega into distance, which is r root 2, but omega r is v. So it is v root 2. Oh, so that is the velocity at this point. Perfect. So what about the velocity at this point? Join a line and make sure that you are going perpendicular to it. That will give me the velocity at that particular point. Let's say that is v3. So how much is v3? Again, I need to know omega and that distance. Again, you can see this is r, this is r, this is r root 2. Look at this triangle. Radius, radius, r root 2. Perfect. The velocity is like this. So omega into r root 2. Omega r is v. So again, v root 2. So that's how easily you can solve these questions by using this concept that since the contact is at rest, It's as if the axis is itself here and the entire body is rotating about this point. Then it makes my job easy. Is this absolutely clear, my dear warriors? Perfecto, amazingo. So some basic concepts of rolling, if you know this much, I think it is more than enough. You don't need to know much, okay, because they don't ask questions on rolling anymore. It has been deleted now from the syllabus. Okay, but still I have given you just in case. Anyways, now let's come to the final point of this chapter, and that is basically called as the conservation of angular momentum. The conservation of angular momentum. It's just like linear momentum conservation, just that instead of momentum you have angular momentum, instead of force you will have torque. That's it, that's the only difference. So think like this, if by any chance you find that the net torque acting on a system is 0. What is torque? A rate of change of angular momentum. So that means dl by dt is going to be 0. This means what? This means only one thing, the angular momentum of that particular system, only a constant's derivative can be 0. So the angular momentum of that system is basically a constant. This is basically law of conservation of angular momentum. If the net torque acting on a body is 0, this is very important. If the net external, this is very important, external, not internal, torque on a body is 0, then the total angular momentum is conserved about that same point, not different point, because torque is measured about a point. You can't go and say angular momentum I will measure about some other point. No, angular momentum is conserved about that point, or basically whatever axis you have taken. Please note, just like before, energy may not be conserved. Energy may be lost, it might be gained. So energy may not be conserved. The most common example of this, say there is a beautiful champa over here and she has some nice weights with her. She is standing on the ground, smooth floor, and she is spinning right now. She is spinning right now with some angular velocity. She is rotating like this. Okay, she is just rotating like this. She is doing some dance. What she does? She is on a smooth surface. Let's assume skating or something. She basically makes her legs go a little bit wider like this, and oops. So this is our beautiful champa. She pulls her hands apart like this. So earlier she was like this. Now she makes her legs and hands like this, and now she starts rotating. In this process, whatever forces were there, they were all internal. They were part of champa only. So all forces were internal. All forces are basically internal. There was no external force. So definitely we can see, because it was a smooth surface, net external torque was 0. And what does our law of conservation of momentum say? If net external torque is 0, then the total angular momentum is conserved. So that means I can say angular momentum of champa is basically a constant. Now what is the formula for angular momentum? It is moment of inertia of champa and multiplied by angular velocity of champa. So think about it. When her hands legs are close, all the masses are close to the axis. But when her hands legs are far, the distance r is more, So won't the moment of inertia increase as she spreads her hands and legs? So if I increases, to keep the product a constant, what should change? If I increases, omega should decrease. So that's why you will see there will be a reduced angular speed. Reduced angular speed. She will not rotate that fast. But if she was already like this and she does this, she will rotate really fast. Why? Because then I will decrease, omega will increase. So that will be very interesting to see. Oh, Champa's hair, we forgot completely. So sorry guys. So here her hair was like this. Now her hair are like this. Even the hair has decided to go away. That is Champa's hair. Yeah. Yeah. Is that clear, everyone? Beautiful, beautiful concept. So let's do a question on this. Say for example, as you can see, there are two disks, mass m, 2m, radius r, 2r, angular speed omega, 2 omega, directions are also different. They are spinning, they are far apart, then you place them on each other. The moment you place them, they will start rubbing each other. One will try to reduce other speed, other will try to increase other speed. Finally, they will rotate like a combined object. So these two disks are placed together on a smooth axis. On a smooth axis. The question is, find the omega final, whatever is that final omega with which they rotate as a combined system. What do you think is that combined omega? Okay. Since the axis is smooth, there is no other torque. mg can't give torque. How can it spin it like this? Normal can't give torque. No other Pandu Champa is there to spin it. So obviously, in this entire scenario, we can clearly say net external torque is 0. Therefore, the angular momentum is going to be constant. So let's write down what is the initial angular momentum, and let's also write down what is the final angular momentum. And let's take one direction as positive, other direction as negative. So for reference, let's take the bigger one as positive. So this is positive. Naturally, the other one will be negative. Okay. So what is the initial angular momentum? This guy will have some angular momentum, that will be I1, and this will be, let's say, I2. So I1 will be negative, I2 will be positive. Finally, they are both together. Sorry, not I1 guys. L1. L1 will be negative, L2 will be positive. Finally, as a combined system, they will have a final angular momentum. Why minus? Because this is negative, this is positive. First guy's angular momentum, I omega, I1 and omega 1, omega 1 is omega. Second guy's angular momentum, I omega again, moment of inertia I2, omega is basically 2 omega. Finally, both of them are together. So combined moment of inertia I1 plus I2 into final angular velocity. Angular momentum formula is I omega. That's all I am using, nothing more, nothing less. What is moment of inertia of this guy? Disk. It is mr square by 2 into omega. What's moment of inertia of this guy? It is 2m, 2r square, which means 4r square by 2 into 2 omega is equal to I1 mr square by 2, I2 2m, 2r whole square, which is 4r square divided by 2, and this whole thing into final omega. mr square cancels. Okay, so I'm left with minus omega by 2 plus 2 cancels, 4 2s are 8, plus 8 omega is equal to 2 cancel, 4 2s are 8, yes, perfect. 2 cancelled, 4 is there, plus half is there, 4 plus half is 4.5, which is 9 by 2. So 9 by 2 omega final. Now this will make it 8 minus half, right? Perfect, which is 7.5, which is 15 by 2. So 15 by 2 omega is equal to 9 by 2 omega final. 2 cancels. So final angular velocity will be 15 omega divided by 9. That is the correct answer. So final angular velocity is 15 omega by 9. Done and dusted. So you get questions like this, discs are spinning. Sometimes one of the discs might be at rest also. So that guy's angular momentum will be 0. And then they will ask you, what is the final speed? Sometimes they might even ask you, what is the energy loss? So if by chance they ask you in this same question, imagine in this same question, find the loss of energy. In this same question, find basically the loss of energy. What will you do? Earlier it had some energy, now it has some new energy. So subtract the two. So the energy loss will be, initially it will be more, finally it is less because it will lose something. So initial minus final. What is initial? Half this guy's moment of inertia, which is mr square by 2 into omega square, plus half this guy's moment of inertia, 2m into 4r square divided by 2 into 2 omega whole square. This is all initial minus final. I is mr square by 2 plus 2r square, which is 4r square by 2. This is the total moment of inertia into final angular velocity. Final angular velocity was 15 omega by 9. So 15 omega by 9 whole square. Solving this, definitely you will get the loss of energy. I want you guys to put the answer as your homework in the comments. Try to solve this particular question, okay, after the class is over, and post the answer in the comment section. Cool. So this is how you do the questions where energy is lost and momentum is conserved. So it's a very simple thing. I into omega is constant. Every question is I omega is constant. Okay, standard formula. So that is the last concept which you should know for rotational motion. That's it. Okay. So guys, yeah, today was, I'm not sure which day it is right now. We started our challenge, right, from Monday, if I'm not wrong. Yeah. So make sure that you put up in the comment section that yes sir, our next day of challenge is done, or basically rotation done, or you can just say rotated, so that I know, fine guys, you have seen the class till the end, and of course your homework question is still there. So make sure you're solving that homework question and putting it up in the comment section. Okay, just try to solve this. So we have covered almost all the concepts and we have done all the basic problems. Obviously more question practice, PYQs, everything will come in the next couple of classes and revision time. But conceptually, I hope you understood all these things about rotation, and I hope things were made very simple. Okay, so take care guys, have a great time, and yes, it's almost like, what is it? Oh, almost 2 o'clock. So almost like a fire class. All right, take care guys. Bye bye. Hasta la vista.